Hello there, and welcome to Physics with William, where curiosity gets cozy, science takes the scenic route, and the universe is allowed to be enormous without being in any hurry about it. Tonight, we're going to drift gently into one of the strangest ideas in modern cosmology, an idea that begins before stars, before planets, before atoms had settled into their familiar shapes, before there was anything like a night sky to look up at and wonder about. We're going to explore what actually happens during cosmic inflation, that tiny, almost impossibly brief moment when the young universe may have expanded with such astonishing speed that ordinary words begin to look a little underdressed for the occasion. And yet, even though cosmic inflation sounds grand and dramatic, with a name that feels as though the universe has been taken to a celestial bicycle pump, the basic question behind it is surprisingly simple. How did everything become so large, so smooth, and so evenly spread out? How did a cosmos that began in a hot, dense, unfamiliar state become the vast and structured universe we see today, with galaxies scattered across space like lanterns seen through deep fog? Why does the universe look so similar in one direction as it does in another, even when those directions are separated by distances so vast that light itself has not had enough time to carry messages between them? These are not small questions. They are the kind of questions that sit quietly at the back of the mind and wait until the room is dark. They are questions that begin with telescopes and mathematics, but somehow end up beside your pillow, because the story of cosmic inflation is also the story of how there came to be a universe with enough space for nights like this, enough time for stars to form, and enough calm little corners for someone to listen while the day loosens its grip. Before we go any further, let me ask you something. Where are you listening from tonight? Are you tucked away in a city where the streetlights are still humming outside the window, or somewhere quieter, where the sky is dark enough to show a few patient stars? Is it late evening for you, or the small hours of the morning? Or perhaps you're listening from a place where the day is only just beginning? It is a fitting question for a story about the earliest universe, because every place on Earth is sharing the same cosmos, yet each of us meets it from our own little patch of time and space. A bedroom, a train seat, a desk lamp, a sofa, a softly glowing screen. Tiny human coordinates inside a universe that once may have grown from smaller than anything we can sensibly picture into something vast beyond all ordinary imagination. If you find this kind of journey soothing, or gently interesting, or simply a nice way to let your thoughts settle after a long day, I would be very grateful if you liked the video, subscribed, or shared this little quiet corner of physics with someone who might enjoy falling asleep beside the universe. It helps the channel continue sending calm science into the night, which is a pleasingly odd thing to say, but there we are. And as always, I do hope the ideas are interesting enough to keep you company, but not so exciting that they keep you awake. Cosmic inflation may be one of the most dramatic events in all of physics, but we shall approach it softly, as one might approach a sleeping cat with a cup of tea nearby. So, settle in, let the shoulders drop a little, let the clock become less important for a while. We're going to begin not with explosions, despite what the phrase Big Bang sometimes suggests, but with expansion. That distinction matters. The early universe was not like a firework bursting into empty space. There was no outside room waiting for the universe to arrive, no dark auditorium into which matter suddenly flew. Space itself was changing. Space itself was stretching. The distances between places were growing, even before there were proper places in the everyday sense. If that sounds difficult to picture, that is perfectly reasonable. The early universe did not consult the human imagination before choosing its behaviour. Cosmic inflation is the name given to a proposed episode of extremely rapid expansion in the very early universe. Not merely fast in the way a rocket is fast, or a meteor is fast, or a sleepy person suddenly hearing their alarm is fast. This was expansion of space itself, happening everywhere at once, with distances increasing at a rate that makes ordinary motion seem almost irrelevant. During inflation, two regions of space were not flying through space away from one another like birds startled from a tree. Rather, the space between them was growing. It is less like raisins moving through dough, and more like the dough itself rising, carrying the raisins farther apart without the raisins needing to make any decisions of their own. Though if raisins ever do begin making decisions, cosmology will have to open a very different department. The idea of inflation was developed to solve several puzzles left behind by the standard picture of the Big Bang. The Big Bang theory, despite its slightly noisy name, is an extraordinarily successful description of the universe expanding from a much hotter and denser past. It explains why distant galaxies are moving away from us, why the universe is filled with a faint afterglow of early heat, and why the simplest chemical elements formed in the proportions we observe. But like many good theories, it raised new questions as it answered old ones. When scientists looked carefully at the universe, they found patterns that seemed almost too neat. The cosmos appeared remarkably smooth on large scales. It appeared very close to flat in its overall geometry, and tiny variations in the early universe seemed to have just the right kind of pattern to grow into galaxies, clusters, and all the great cosmic architecture we see today. Inflation was proposed as a way to explain how this could happen. It says that long before the universe became old enough for atoms, stars, or even light to move freely through space, there was a brief period when the universe expanded at an extraordinary rate. A small region, perhaps one that had once been connected and able to settle into a fairly uniform state, was stretched until it became enormous. Any wrinkles or irregularities were smoothed out, much as the surface of a balloon becomes smoother as it is inflated. That image is useful, though not perfect. The universe is not expanding into a room, and there is no cosmic child standing nearby holding the knot. Still, the balloon gives us a hint. Stretch something enough, and small curves flatten. Local unevenness becomes diluted. Tiny features become spread across vast distances. This is one of the central reasons inflation is so appealing. It takes a universe that might have begun in a messy or puzzling state and gives it a way to become the kind of universe we observe. Smooth, but not perfectly smooth. Flat, but not featureless. Uniform enough to be understood, yet textured enough to become interesting. And we should be rather grateful for that last part. A perfectly smooth universe would be elegant, perhaps, but deeply dull. No galaxies, no stars, no planets, no late-night cups of tea, no one wondering about cosmic inflation while trying to get comfortable under a blanket. The little imperfections matter. They are the seeds from which structure grows. During inflation, tiny quantum fluctuations, the small restless uncertainties present in fields at the smaller scales, may have been stretched to cosmic size. What began as microscopic tremors became the faint unevenness in density that later gravity could work with. Places that were just a little denser than average pulled in more matter over time. Those regions became the beginnings of galaxies and clusters. Places that were slightly less dense became great cosmic voids. In this way, inflation offers a remarkable bridge between the very small and the very large. The same strange quantum behavior that usually belongs to the hidden world of particles may have left fingerprints across the entire sky. That idea is almost comically bold. It says that the arrangement of galaxies across the universe, the grand map of cosmic structure, may have begun as tiny quantum ripples during the earliest instant of cosmic history. The universe we see now, full of spirals and clusters and glowing clouds, may carry the memory of microscopic fluctuations that were stretched beyond recognition. It is as though the cosmos took the tiniest whisper and amplified it into architecture. But what was doing the stretching? What caused inflation to happen? In many versions of the theory, the answer involves something called the inflaton field. A field in physics is something that has a value throughout space. We are familiar with fields even if we do not always call them that. A magnetic field can guide a compass needle. A gravitational field tells objects how to fall. The inflaton field is a proposed field that, in the early universe, may have carried a special kind of energy capable of driving rapid expansion. It is not something anyone has placed in a jar or seen directly in a laboratory. It is a theoretical ingredient introduced because it can help explain how inflation might work. The inflaton field is often imagined as being temporarily stuck in a high-energy state. While it remained there, its energy acted in a way that caused space to expand extremely quickly. Then, as the field changed and settled into a lower energy state, inflation ended. The energy that had driven the expansion was transformed into particles and radiation, filling the universe with the hot material that would later evolve according to the more familiar Big Bang picture. In this sense, inflation is not exactly a replacement for the Big Bang. It is more like a possible prologue, a strange opening act that prepares the stage for the hot expanding universe that follows. That is an important point, because people sometimes imagine inflation as a separate explosion before the Big Bang, as if the universe first did one dramatic thing and then another, like a cosmic theatre production with an over-enthusiastic lighting crew. But many cosmologists think of inflation as part of the earlier story of the Big Bang universe. It helps explain the conditions from which the hot, dense, expanding phase emerged. After inflation ended, the universe was filled with energy, heat, and particles. From there, the familiar sequence could unfold. Particles formed, matter and antimatter interacted. Simple nuclei appeared. Much later, atoms formed, and light was finally able to travel freely. Later still came stars, galaxies, planets, and eventually small mammals with calendars. There is something humbling about this. The universe did not become understandable all at once. It changed through stages, each one leaving traces for later beings to discover. Cosmic inflation belongs to a time so early that no telescope can show it directly. We cannot simply look back and watch it happen, because the universe was far too hot and opaque in its youth. Light from those earliest moments could not travel freely to us. The oldest light we can observe directly is the cosmic microwave background, a faint glow released much later, when the universe cooled enough for atoms to form and light could finally move without constantly scattering. That glow is like a baby picture of the universe, though by cosmic standards it was already far older than the inflationary moment itself. Still, the cosmic microwave background may preserve clues. It is astonishingly uniform, but not perfectly so. It contains tiny temperature differences, small variations that match what inflation predicts with impressive success. These variations are like a pattern frozen into the early light of the cosmos. By studying them, scientists can test ideas about inflation, refine models, and ask whether the theory is pointing towards something real about the earliest universe. The evidence is not a simple signed note from the cosmos saying, yes, inflation definitely happened. The universe, unfortunately, is poor at paperwork. But the patterns we observe are strongly consistent with the broad inflationary picture, which is one reason the idea has become so influential. At the same time, inflation is not a finished story. It is more like a family of possible stories, all sharing the idea of rapid early expansion but differing in the details. What exactly was the inflaton field? How did inflation begin? How did it end? Did it happen only once in the region that became our observable universe? Or could inflation continue elsewhere, giving rise to many regions with different properties? These questions are still debated. Cosmology, at its best, is not a list of things we know perfectly. It is a careful conversation between theory and observation, between what the equations suggest and what the sky allows. That makes inflation a particularly fascinating topic for a quiet evening. It is one of those ideas that sits at the boundary between deep confidence and deep mystery. It explains a great deal. It fits many observations, yet it also points beyond what we can directly see. It asks us to imagine a time when space itself behaved in a way that feels almost impossible from the viewpoint of everyday life. We are used to objects moving through space. Inflation asks us to think about space expanding so quickly, that the idea of objects moving becomes less important than the growth of the stage itself. Imagine marking 2 points on a soft rubber sheet, and then stretching the sheet. The points become farther apart, though neither point has crawled across the rubber. Now imagine that happening not to a sheet, but to space in every direction. Not from a centre, but everywhere, with every small patch of space swelling into a much larger patch. This is not an exact picture, but it helps loosen the mind from the common mistake of thinking the universe expanded from a single location into surrounding emptiness. There was no centre of the expansion in the ordinary sense. Every region saw other regions move farther away because the space between them increased. This can feel strange because our brains evolved for a world of furniture, weather, food, and occasionally trying to remember why we walked into a room. We are good at thinking about things inside space, but less comfortable thinking about space itself as dynamic. Yet this is one of the great lessons of modern physics. Space is not merely a passive container. It can expand, it can curve, it can carry waves, it can shape the motion of matter and light. During inflation, space may have done something even more dramatic. It may have grown with a kind of runaway intensity, turning an incredibly tiny region into the vast seed of everything we can observe. The phrase observable universe is important here. When cosmologists speak of the universe we can observe, they mean the region from which light has had time to reach us since the early universe became transparent. There may be much more beyond that horizon, perhaps vastly more. Inflation makes this idea feel natural, because it can stretch space so much that our observable patch is only a small part of a larger whole. We should not imagine ourselves at the middle of all existence peering out from the privileged centre. We are more like someone standing in a field on a foggy morning, able to see only so far while the landscape continues beyond the mist. And that brings us back to the quiet wonder of the topic. Cosmic inflation is not merely a technical patch added to cosmology. It changes the way we picture our place in the universe. It suggests that the smoothness of the sky, the vastness of space, and the very seeds of structure may all trace back to a moment of extreme expansion in the earliest fractions of cosmic history. It offers a reason why the universe looks orderly enough for science to work, yet irregular enough for worlds to exist. It links the smallest uncertainties to the largest patterns. It turns a fleeting instant into a source of everything that followed. There is a gentle irony in that. The period of inflation, if it happened, lasted for an almost unimaginably short time, brief beyond ordinary comparison. Yet its consequences may have shaped the entire visible cosmos. A moment too short to experience, even if there had been anything around to experience it, may have determined the grand layout of space. It is a reminder that importance is not always measured by duration. Some things happen quickly and leave behind a universe. So tonight, as we begin moving into this story, we will not rush toward the deepest technical details. We will let the idea unfold slowly. First, we will picture the early universe and the puzzles that made inflation necessary. Then we will look at what expansion means when it is space itself that grows. We will meet the strange proposed field that may have powered this event, follow the quantum ripples that became cosmic structure, and eventually look for the faint traces of inflation in the oldest light we can see. Along the way, we will keep the language calm, the pace gentle, and the universe at a comfortable distance, which is considerate of it given its size. For now, hold on to the basic image. The universe was once far hotter, denser, and younger than it is today. In its earliest known story, something may have caused space to expand with extraordinary speed. That expansion smoothed and stretched the cosmos, setting up the conditions for everything that followed. Without inflation, the universe we observe would be harder to explain. With it, many of its most puzzling features begin to make sense, though the explanation opens new doors into deeper mystery. And perhaps that is what makes cosmic inflation such a fitting subject for a sleepy journey through physics. It begins with a puzzle, offers a beautiful answer, and then leaves us with larger questions waiting quietly beyond the edge of certainty. Not frightening questions, not urgent ones, just the kind that can rest beside you in the dark, like stars behind a curtain. How did space begin to grow? Why did it grow in just the right way? What did the earliest universe feel like, if feeling had been possible before there were minds, bodies, or even atoms? What happened in that first breath of cosmic expansion, when the small became immense and the future quietly made room for itself? The answer begins with the realization that the Big Bang, on its own, leaves us with a universe that is almost too well behaved. The sky is too even. Space is too flat. Distant regions are too similar. Tiny irregularities are too neatly arranged. Something seems to have prepared the cosmos before the familiar hot expansion took over, and inflation is the leading idea for what that preparation may have been. It is the universe smoothing its blanket before a very long sleep, though admittedly the blanket later developed galaxies, black holes and tax paperwork, so the metaphor can only be taken so far. Still, as metaphors go, it will do for the moment. A young universe stretched rapidly. A hot beginning made possible by an earlier burst of expansion. A sky whose oldest light still carries faint clues. And here we are, much later, listening from our small places on a rocky planet, trying to understand how everything grew large enough to contain us. To understand what cosmic inflation is supposed to do, we need to move backward in our imagination, past galaxies, past stars, past the first atoms, past even the time when light could travel freely through space. We need to go to a universe so young that our usual pictures start to fail us. Not because the universe was being secretive, though it does often give that impression, but because the conditions were so extreme that ordinary experience has almost nothing helpful to offer. There were no planets, no sunlight, no empty darkness with objects floating through it. There was not even a clear stage on which things could be placed in the way we usually imagine them. There was only the early universe itself, hot, dense, changing quickly, and filled with energy in forms that are still difficult to describe with complete confidence. When people hear that the universe began very small, it is tempting to imagine all the galaxies packed into a little ball, sitting somewhere in a larger empty room. Perhaps a glowing bead, perhaps a cosmic seed, perhaps something you might lose under a sofa if you were careless with reality. But that picture is misleading. The early universe was not a tiny object expanding into pre-existing space. Space itself was part of what was small, or at least the region of space that would one day become everything we can observe was incredibly compressed. There was no outside edge that you could stand beyond and watch from a safe distance. No viewing platform, no cosmic balcony. The universe did not begin as a lump inside a room. The room was part of the lump, if we may use such a homely image for something that makes the mind work rather hard. This distinction matters because it changes the whole feeling of the story. The Big Bang was not an explosion at one place, it was an expansion of everywhere. Every point in the early universe was close to every other point, and as the universe expanded, distances between points increased. If you imagine dots painted on a stretchy surface, the dots move apart as the surface stretches, even though none of them is racing across the surface in the ordinary sense. That picture is useful, as long as we remember that the universe is not really a flat sheet and there is not a hand stretching it from the side. Still, it helps us step away from the idea of a central blast. The expansion happened throughout space. Wherever you were, if there had been a you, the rest of the universe would have seemed to be spreading away. Of course, in the very earliest moments there was no you, no observers, and no familiar matter. The ingredients of the universe were not yet arranged into the particles and atoms we know from ordinary life. At such extreme heat and density, matter does not behave like little solid bits. It behaves according to deeper rules, with particles appearing, interacting, transforming, and vanishing in a restless sea of energy. Even the forces of nature may not have had the separate personalities they show today. In our present universe, gravity, electromagnetism, and the nuclear forces each have their own roles. Gravity gathers stars and bends the paths of planets. Electromagnetism holds atoms and molecules together, lights our lamps, and occasionally makes socks cling to laundry with unnecessary drama. The nuclear forces work inside atomic nuclei, shaping the heart of matter. But in the earliest universe, the story may have been different. At very high energies, some of these forces may have been unified, behaving as aspects of a deeper underlying order. Scientists try to reconstruct this early state by combining observation, theory, and particle physics. We cannot build the early universe in a laboratory, which is probably fortunate for laboratory safety committees, but we can recreate tiny pieces of high-energy behavior in particle accelerators and study the conditions that would have existed shortly after the beginning of the hot Big Bang phase. We can also look outward, because looking into space is also looking back in time. Light from distant galaxies has taken a long time to reach us. The oldest light we can see directly is the faint microwave glow released when the universe cooled enough for atoms to form, but inflation, if it happened, came much earlier than that glow. Its traces must be found indirectly, in patterns left behind, like footprints in snow after the person who made them has long since gone inside for tea. The tiny beginning before everything grew is not tiny in the way a marble is tiny. It is more like saying that the whole observable cosmos, everything now visible to our telescopes in every direction, was once compressed into a region far smaller than anything we can picture with comfort. But even here, we must be careful. The observable universe does not mean the entire universe. It means the portion from which light has had time to reach us. There may be much more beyond what we can see, perhaps vastly more. Inflation makes that possibility feel quite natural. The region that became our observable universe might have been a small patch within a much larger reality. When we say that our observable universe was once tiny, we are describing the history of our visible cosmic neighborhood, not necessarily drawing a border around all existence. This is where the imagination begins to feel the strain. If everything we can observe today was once contained in an extremely small region, then that region must have been unimaginably energetic. Heat was not heat in the cozy sense of a blanket or a cup of cocoa. It was heat as a measure of wild motion and intense interaction. Particles did not sit quietly in place. Fields were excited. Energy was packed into space. Conditions changed so rapidly that even the word moment feels too slow and relaxed, like describing a lightning strike as a short appointment. And yet, for all the intensity, the early universe also had a remarkable simplicity. Not simplicity in the sense of being easy, because it most certainly was not easy. Simplicity in the sense that the universe was more uniform than it would later become. Today the cosmos is full of structure. There are galaxies, clusters of galaxies, stars, planets, clouds of gas, empty voids, and dense knots of matter. The universe has texture. But in the deep early past, before gravity had time to amplify small differences, matter and radiation were spread much more evenly. There were tiny variations, yes, and those tiny variations were crucial. Without them, gravity would have had nothing to gather. But compared with the clumpy universe of today, the young universe was extraordinarily smooth. This smoothness is one of the clues that leads us toward inflation. If the early universe began in a small enough region, then different parts of that region could have been in contact with one another. They could have exchanged energy. They could have settled into similar conditions. Then, if inflation rapidly stretched that region, the smoothness would be carried outward and enlarged. A small, well-connected patch could become an enormous observable universe that still looked almost the same in all directions. It is rather like taking a tiny portion of fabric that is fairly even and stretching it until it covers a much larger area. The little imperfections remain, but they are spread out. The overall look becomes remarkably uniform. Before inflation was proposed, cosmologists had a puzzle. The universe looks very similar in opposite directions across the sky. The temperature of the oldest light is nearly the same everywhere. But in the standard hot Big Bang picture without inflation, some of those distant regions should never have had enough time to exchange information. They are too far apart for light to have travelled between them before that ancient glow was released. So why do they have almost the same temperature? How did they coordinate so well? It is as though people on opposite sides of a vast concert hall, unable to hear or see one another, somehow tuned their instruments to the same note. Either there was an unexplained coincidence, or something earlier brought those regions into shared conditions before spreading them apart. Inflation gives a possible answer. It says that the regions now widely separated in the sky were once close together before the rapid expansion. They had a chance to become similar, and then inflation stretched them far beyond each other's reach. The sameness we observe is not mysterious if it was established before the stretching occurred. The universe did not need to send messages across impossible distances later. The agreement was already built in when the visible cosmos was still part of a much smaller connected patch. This idea changes the meaning of the tiny beginning. It was not merely small, it was causally connected, meaning different parts could influence one another. In everyday life, this seems ordinary. One side of a room can affect the other because light, sound, and air can cross the distance. In the early universe, the distances were small enough that energy and information could spread through the region that would become our observable cosmos. Then inflation took that region and expanded it dramatically. The connection came first. The vast separation came later. There is another reason the tiny beginning matters. It helps explain why space today appears so close to flat on very large scales. Flatness here does not mean flat like a table, and it certainly does not mean the universe is a pancake, though pancakes do have their place in a calm discussion. In cosmology, flatness refers to the overall geometry of space. A curved universe can behave differently from a flat one, especially over enormous distances. Observations show that, as far as we can measure, the large-scale universe is extremely close to flat. Without inflation, this would require the early universe to have started with an incredibly precise balance. Too much curvature one way or the other, and the universe today would look very different. Inflation naturally pushes space toward flatness in the observable region. Stretch a curved surface enough, and any small portion looks flatter. The surface of Earth is curved, but the floor beneath your feet looks flat because you're seeing only a small patch. In a similar spirit, inflation can stretch space so much that any initial curvature becomes nearly impossible to detect across our observable universe. The geometry is not necessarily flat everywhere in some absolute sense, but our visible patch can become so stretched that it appears flat to us. This is another reason inflation is so useful. It turns a puzzling fine balance into a natural result of rapid expansion. Still, when we speak of the earliest moments, we reach a boundary of knowledge. If we go far enough back, our current theories stop being fully reliable. General relativity describes gravity and the expansion of space with extraordinary success on large scales. Quantum physics describes the behavior of particles and fields with astonishing precision on small scales. But the earliest universe was both extremely small in relevant ways and dominated by gravity at extreme energies. To describe it fully, scientists would need a theory that combines quantum physics and gravity. Such a theory remains unfinished. This means there may be a deep, earliest era about which we must speak carefully. We can say what our best models suggest after a certain point, but the absolute beginning, if that phrase even makes sense, remains hidden behind the limits of present physics. This caution is important. Science is strongest when it knows where the floor becomes foggy. Cosmic inflation is a powerful idea, but it does not allow us to claim that we understand everything about the origin of the universe. It gives a possible account of a very early expansion and explains several observed features of the cosmos. It does not by itself answer why there is something rather than nothing. it does not tell us with certainty what happened at the very first instant. It does not let us peek outside the universe, if outside is even a meaningful word here. It is a theory about an early physical process, not a magic window into every ultimate question. This may be slightly less dramatic, but it is much more honest, and honestly, the universe is dramatic enough without our help. The tiny beginning also asks us to think differently about scale. In everyday life, small things are usually simple and large things are complicated. A grain of sand is simple compared with a beach. A single note is simple compared with a symphony. But the early universe reverses this intuition. The small region that became our observable cosmos contained the potential for everything we now see: galaxies, stars, planets, chemistry, life, weather, oceans, books, sleepy conversations about cosmology. All of it depended on the conditions in that early state. Not because the early universe contained these things in miniature, like a tiny model village tucked inside a cosmic egg, but because it contained the fields, energy, and initial variations from which later complexity could grow. A helpful way to think about this is to imagine a patch of soil before anything has sprouted. At first glance, it may look plain, but within it are seeds, nutrients, moisture, and conditions that can lead to a forest if time and circumstance allow. The early universe was not a forest. It was not even seeds in a literal sense, but it carried the conditions from which structure could develop. Inflation, in this picture, prepared the ground by stretching the patch and distributing tiny variations across it. Later, gravity would act slowly and patiently, gathering matter into the first large structures. Stars would ignite. Heavy elements would be made in stellar interiors and explosions. Planets would form from enriched material. Chemistry would become more elaborate. Life, at least in one small place we know of, would appear and eventually invent bedtime physics. The smallness of the early universe can also mislead us about time. We tend to imagine that important events require long durations. Mountains take ages to rise. Stars live for millions or billions of years. Evolution works over vast stretches of biological history. But inflation, if it happened, was extremely brief. Its shortness does not make it unimportant. A match can light a candle in an instant. A camera flash can capture a scene. A small change at the beginning of a process can shape everything that follows. In cosmology, early conditions matter enormously because the universe evolves from them. Inflation may have been brief, but it could have stretched space, shaped geometry, smoothed irregularities, and created the primordial seeds of structure. The idea that quantum fluctuations could become the seeds of galaxies is especially striking. In the early universe, fields were not perfectly still. Quantum physics tells us that even empty space is not truly empty in the simple, everyday sense. Fields can fluctuate. Tiny variations can appear. During inflation, these small fluctuations would have been stretched along with space. Once stretched to huge scales, they became differences in density. Some regions contained slightly more energy than others. These differences were tiny, but gravity is patient. Over time, the denser regions attracted more matter. They became the beginnings of the cosmic web, the vast network of galaxies and clusters we observe today. So the tiny beginning was not perfectly smooth. It had just enough unevenness. This is a delicate and wonderful point. A universe that was too lumpy early on might have collapsed into black holes, or become wildly irregular. A universe with no fluctuations at all would remain bland and structureless. The universe we inhabit seems to have had a fine texture, smooth enough to be stable on large scales, uneven enough to become interesting. Inflation offers a mechanism for producing exactly this kind of texture. It does not have to place galaxy seeds by hand. It takes natural quantum fluctuations and stretches them into the stage on which gravity can later perform its long, slow work. There is a quiet strangeness in the fact that our existence may depend on small imperfections. We often think of perfection as smoothness, balance, total order. But a perfectly even early universe would not have produced the structures needed for life. We are here because the universe was not perfectly uniform. The slight wrinkles mattered. The little differences mattered. Every galaxy is, in a sense, an old consequence of the universe not being completely tidy. This is comforting, in a small human way. Even the cosmos needed a few irregularities to become itself. The tiny beginning before everything grew is therefore not a simple dot, not a known absolute first moment, and not a miniature version of the present universe. It is a state of extreme density and energy, possibly preceded or shaped by conditions we do not yet understand, in which the region that became our observable universe was compact enough to share common properties. Then inflation, according to the theory, expanded that region enormously. It took a connected patch and made it vast. It took quantum fluctuations and stretched them into cosmic patterns. It took whatever curvature or unevenness existed and diluted much of it. It made the universe appear smooth, flat, and similar across enormous distances, while preserving the tiny variations that would later grow into structure. And as we keep following this thread, we should remember that inflation was not invented because scientists wanted the universe to sound more exciting. It was proposed because the ordinary hot Big Bang picture, successful though it is, left behind serious puzzles. The tiny beginning helps us see why. If the universe was once compact, hot, and connected, and if it then expanded in the usual way, certain features of the cosmos remain difficult to explain. Why is the oldest light so evenly matched across the sky? Why does space look so flat? Why are there no obvious relics from certain high-energy theories, relics that might otherwise have been expected? Why do the small fluctuations have the particular pattern we observe? These questions do not break the Big Bang theory, they deepen it. They ask what came before the familiar hot expanding phase, or what shaped its initial conditions. Inflation enters as a possible answer, not by replacing the Big Bang, but by explaining why the Big Bang universe began the part we can study in such a special state. It is a prelude to the hot beginning, a rapid stretch before the slower unfolding. It says that the universe was prepared, not by intention, but by physics. So when we picture the tiny beginning, we are not picturing a little fireball in empty space. We are picturing an early state of space and energy itself, where the future observable universe was compressed into a region small enough for conditions to be shared. We are picturing a universe before atoms, before light could move freely, before gravity had built the first structures. We are picturing a stage before scenery, a recipe before ingredients had separated into familiar forms, a beginning not yet filled with objects but rich with potential. Then, according to inflation, that small connected region began to stretch with astonishing speed, and the features of our universe were carried outward with it. This is where the story begins to press against the limits of ordinary imagination again. Expansion is already strange enough when applied to space. Rapid expansion in the earliest universe is stranger still. But the next step is to ask why such an idea was needed in the first place. What was wrong with simply saying that the universe was hot, dense, and expanding? Why did cosmologists feel that something more had to be added? The answer lies in the details of the sky itself, in the smoothness that seems too smooth, the flatness that seems too precise, and the distant regions that appear to have agreed with one another before they should ever have had the chance. That is the point where the familiar story begins to look a little too neat. The Big Bang picture tells us that the universe was once much hotter and denser than it is today, and that space has been expanding and cooling for billions of years. This idea is one of the great successes of modern science. It explains why distant galaxies appear to be moving away from us. It explains why the universe contains a faint leftover glow from an early hot state. It explains why the lightest elements, especially hydrogen and helium, were made in the early universe in proportions that match what we observe. It gives us a grand outline not of an explosion into space, but of space itself growing, cooling, and changing over time. So the question is not whether the Big Bang picture failed. It did not. It worked beautifully. In many ways, it worked so well that it became the foundation on which the rest of modern cosmology was built. But a successful theory can still leave behind questions. A map can guide you through a city and still not explain who built the roads. A clock can tell you the time and still not explain why you're awake at 3 a.m. thinking about the origin of the universe. The Big Bang picture described how the universe evolved once it was already hot, dense, expanding, and remarkably uniform. What it did not fully explain was why the universe began that part of its story with such special conditions. This is where cosmic inflation enters, not as a rival to the Big Bang, but as an added earlier idea, a way of explaining how the hot Big Bang universe got started in such an orderly way. It is a little like finding a perfectly arranged dinner table and realizing that the meal itself may explain what happens next, but not how all the plates, glasses, napkins, and mysteriously tiny forks ended up in place before anyone sat down. The Big Bang tells us what the universe did once the table was set. Inflation asks how the table came to be set so evenly across the cosmic dining room. The first great puzzle is the smoothness of the universe. When astronomers look at the oldest light we can observe, the cosmic microwave background, they find that it is almost the same temperature in every direction. This glow comes from a time when the universe had cooled enough for atoms to form and light could finally travel freely. It is not light from the very first instant, but it is ancient enough to serve as one of our best windows into the early cosmos. And what it shows is astonishing. No matter where we look in the sky, the temperature of this ancient light is nearly identical. There are tiny differences, and those tiny differences matter very much, but overall the uniformity is extraordinary. At first, this might sound like a small detail. The universe is smooth, very nice. Perhaps it had a good morning routine, but in cosmology, this smoothness is a serious clue. Regions on opposite sides of the visible universe are so far apart that, in the standard hot Big Bang picture without inflation, they should never have been able to exchange light, heat, or information before the cosmic microwave background was released. They were outside each other's causal reach. In ordinary language, they should not have had time to talk to one another, yet they appear to have settled on almost exactly the same temperature. Imagine walking into a large house with 100 rooms, each sealed off from all the others. No one can pass messages between them. No sound travels through the walls. No heating system connects them. And yet, when you open the doors, every room is at almost precisely the same temperature. You would not be wrong to raise an eyebrow. You might suspect that, before the doors were sealed, the rooms were once connected. Perhaps they were once part of one open space, allowed to come into balance before walls were suddenly placed between them. Inflation offers a cosmic version of that idea. It says that regions now separated by vast distances were once close enough to interact, and only later were they stretched far apart. This is known as the horizon problem, though we do not need the term to understand the puzzle. Horizon in cosmology is a boundary of possible communication. It marks how far light or any influence could have travelled within a given time. If two regions are beyond each other's horizon, they cannot have exchanged signals. Without inflation, the early universe seems to contain regions that look coordinated even though they should never have been in contact. Inflation solves this by making the observable universe come from a once small connected patch. That patch could reach a common state. Then rapid expansion stretched it until its parts were separated across the sky. The agreement we see today was not arranged across enormous distances. It was inherited from a much smaller beginning. The second puzzle is the flatness of the universe. This word can be confusing because it invites the wrong picture. When cosmologists say the universe is flat, they are not saying it is shaped like a sheet of paper or a table. They are talking about the geometry of space on very large scales. In a curved geometry, the rules of distance, angles, and parallel lines behave differently than they do in ordinary flat space. The universe could have been strongly curved one way or another, depending on its total energy and expansion. But observations show that the large-scale universe is extremely close to flat. Again, this might sound like a tidy but harmless fact. The universe is flat enough. Wonderful. Put that on the cosmic inspection report. The difficulty is that, in the standard Big Bang picture without inflation, flatness is unstable in a way. If the early universe had been even slightly away from the precise balance needed for near flatness, that small departure would have grown over time. By now, the universe would look very curved, or it might have expanded too quickly, or collapsed long ago, depending on the exact conditions. To get a universe as flat as ours appears today, the early universe would have needed to begin with an astonishingly exact balance. This is the kind of thing physicists notice. Nature can certainly contain precise conditions, but when a theory requires the early universe to be adjusted with extreme delicacy for no obvious reason, scientists begin to wonder whether something deeper is going on. It is like balancing a pencil perfectly on its tip and then finding it still upright hours later. You could say it was just placed very carefully, or you might suspect there is a hidden support. Inflation provides that hidden support. Rapid expansion stretches space so much that any initial curvature becomes diluted across the region we can observe. A small patch of a curved surface can look flat if it is enlarged enough. You know this from standing on Earth. The planet is round, but the ground beneath your feet does not feel round. Your little local patch seems flat because the curve is spread over a large distance. Inflation applies a similar idea to the early universe. Whatever curvature may have existed in the original patch, expansion stretched it until our visible region became nearly flat. Instead of requiring the universe to begin with an almost impossibly precise geometry, inflation makes near flatness a natural result. The third puzzle is about unwanted relics. Some theories of very high-energy physics suggest that the early universe should have produced strange heavy objects or defects as it cooled. These hypothetical relics would be leftovers from transitions in the behavior of fields, a bit like cracks forming in ice as water freezes, though the actual physics is much stranger and less likely to be found in your freezer. If such relics were made in large numbers, we might expect to find evidence of them today, but we do not see them in the amounts that some theories once suggested. Inflation can help here too. If such relics existed before or during the early stages of inflation, the rapid expansion would dilute them enormously. They would be spread so far apart that our observable universe might contain none of them at all, or so few that they would be extremely difficult to detect. This is one of inflation's quieter talents. It does not merely smooth and flatten, it also cleans house. It takes anything rare and heavy and stretches space until those things become practically absent from our visible patch. A cosmic tidying service, though admittedly one that operates by expanding reality rather than putting things in drawers, the fourth puzzle is perhaps the most fruitful of all. The universe is smooth, but not perfectly smooth. The cosmic microwave background contains tiny temperature variations, subtle differences from one direction to another. These are not mistakes. They are the most important tiny wrinkles in the sky. Without them, matter would have been distributed too evenly for gravity to build galaxies. With them, slightly denser regions could attract more matter, growing over time into the cosmic structures we see today. The question is where those tiny variations came from, and why they have the pattern we observe. Inflation gives an elegant answer. During the inflationary period, quantum fluctuations in the fields of the early universe would have been stretched to enormous scales. At the smallest levels, fields are never perfectly still. They have unavoidable fluctuations, little variations built into quantum physics. Under ordinary circumstances, these fluctuations remain tiny. But during inflation, space expanded so rapidly that microscopic variations could be stretched across cosmic distances. Once stretched, they became differences in density. Later, gravity amplified those differences into galaxies and clusters. This is one of the most remarkable parts of the inflationary idea. It does not merely solve problems by smoothing everything out. It also explains why the universe was not smoothed out completely. Inflation creates a universe that is mostly uniform, but lightly textured. It provides the seeds of structure while explaining the overall smoothness. That balance is exactly what our universe seems to need. Too much irregularity and the cosmos might have been chaotic and hostile to the formation of stable structures. Too little irregularity and there would have been no stars, no galaxies, no planets, and no listeners wondering whether they should have made tea before pressing play. The Big Bang picture alone could describe the growth of these fluctuations after they existed. It could show how gravity would make small density differences larger over time. But it did not fully explain the origin of the initial pattern. Inflation links that pattern to quantum physics in the earliest universe. Tiny fluctuations became cosmic blueprints. That idea connects the smallest known kind of physical behavior with the largest structures in existence. It is a bridge so bold that it almost sounds like something invented for a story, and yet the patterns observed in the cosmic microwave background fit this inflationary picture with impressive accuracy. This is why the Big Bang needed a bigger idea. Not because it was wrong, but because it began its main explanation after the most puzzling initial conditions were already in place. It told us the universe expanded and cooled. It told us how light elements formed. It told us why ancient radiation still fills space. But it did not, on its own, explain why the early universe was so uniform across disconnected regions, why it was so flat, why certain predicted relics are not seen, or why its tiny irregularities had just the right character to grow into cosmic structure. It is worth pausing here, because the phrase Big Bang can create a false sense of completeness. It sounds like the name of an event, a single dramatic beginning, a cosmic crash symbol at the start of everything. But in modern cosmology, the Big Bang model is really a description of the universe's hot, dense, expanding history. It does not necessarily describe the absolute beginning of existence. It does not tell us what happened at the deepest first moment, if there was one. It does not explain every initial condition. It is a powerful model of cosmic evolution, not a final answer to every question that can be asked about origins. Inflation was introduced to push the explanation further back. It suggests that before the hot Big Bang phase, or at least before the earliest ordinary hot expansion we can confidently describe, the universe went through a period dominated by a special kind of energy that caused space to expand extremely quickly. Then inflation ended, and that energy was converted into particles and radiation, filling the universe with heat. This transition set the stage for the hot Big Bang evolution. So when someone says inflation happened before the Big Bang, they often mean before the hot, particle-filled stage usually associated with the Big Bang picture. The wording can be slippery, because different scientists use the phrase Big Bang in slightly different ways. But the important point is that inflation acts like a prelude that explains why the hot early universe began with the conditions it had. Think of the standard Big Bang model as beginning with a pot already full of hot soup, simmering and expanding in a very unusual kitchen. It can tell you how the soup cools, how ingredients combine, how the steam fades, and eventually how leftovers become galaxies, if we are willing to stretch the kitchen metaphor beyond all reasonable culinary limits. But it does not fully explain who prepared the soup so evenly in the first place. Inflation says that the contents were once part of a much smaller region, smoothed and then rapidly stretched, before being reheated into the hot state the Big Bang model describes. This does not answer every question about the kitchen, the chef, or why there is soup rather than no soup, but it explains some otherwise puzzling features of the meal. One reason inflation became so influential is that it made predictions that could be compared with observation. A good scientific idea does more than sound satisfying. It must risk being wrong. Inflation predicts a universe that should be very close to flat. It predicts small density variations with a particular kind of pattern, nearly the same strength across many different scales but with slight differences. It predicts that these variations should be mostly random in a very specific statistical sense, like a natural quantum origin stretched across the sky. Observations of the cosmic microwave background have matched many of these broad predictions extremely well. This does not mean every version of inflation is confirmed. There are many inflationary models, and some have been ruled out or made less likely by observations. The details remain uncertain. Scientists still debate what field drove inflation, what its energy was, how long the process lasted, and exactly how it ended. Some versions predict faint gravitational wave patterns from the earliest universe, a kind of deep ripple in space itself. Searches for these signals continue, and finding them would provide an extraordinary new clue. Not finding them at certain levels also helps narrow the possibilities. Science advances both by discovery and by careful disappointment, which is less glamorous but very useful. Another reason the Big Bang needed inflation is that the early universe seems to have had a special arrow of development. It began in a low entropy state compared with what it could have been. Entropy is often described as disorder, though that simple word does not capture all the subtleties. The key idea is that the universe has been evolving from a more ordered early condition towards states with greater overall entropy. Inflation may not fully solve the deep mystery of why the universe had such a low entropy beginning, but it reshapes the question. It can make a small, smooth patch grow into a large, smooth, observable universe, and it can explain how structure-producing fluctuations were laid down. The deeper question of why inflation itself began remains open, like a quiet door at the back of the theory. This is important because inflation is not a magic spell that removes all mystery. It solves certain problems very well, but it also asks for its own explanation. Why was there an inflaton field? Why did it have the right properties? Why did it start in a state that allowed rapid expansion? How did it transition into the hot universe afterward? These are serious questions. Some scientists view them as natural next steps. Others worry that inflation can be flexible enough to fit many outcomes, making it harder to test in a simple way. The debate is part of the living science of cosmology. Inflation is powerful, widely studied, and strongly supported by several lines of evidence. But it is not a completed photograph of the earliest reality. Still, its appeal is easy to understand. Without inflation, the universe looks strangely fine-tuned. With inflation, several independent puzzles begin to point toward the same event. Smoothness, flatness, missing relics, and primordial structure all become consequences of rapid early expansion. That is rare and beautiful in science. A single idea reaches into different corners of the problem and finds them connected. It is as though 4 separate locked doors open with the same key. Naturally, scientists then want to inspect the key very carefully, ask who made it, whether it fits perfectly, and whether there are any other keys hidden under the cosmic doormat. The smoothness problem shows us that distant regions needed a shared origin. The flatness problem shows us that space needed an explanation for its large-scale geometry. The relic problem shows us that certain unwanted leftovers needed to be diluted. The structure problem shows us that the universe needed tiny seeds with the right pattern. Inflation offers a way for all of this to happen before the hot Big Bang story unfolds. It stretches a small connected region until it becomes enormous. It flattens the visible patch. It thins out rare relics. It magnifies quantum fluctuations into the first density variations. The phrase bigger idea is fitting, because inflation is literally an idea about the universe becoming much bigger very quickly. But it is also bigger in another sense. It expands the conceptual frame of cosmology. It tells us that the hot early universe may not be the first scene we should imagine. There may have been an earlier physical process that set the stage, shaped the initial conditions, and left traces in the oldest light. The Big Bang is not discarded. It is given a deeper backstory. This happens often in science. A good theory works within a certain domain, and then a deeper theory explains why it works and where its assumptions came from. Newton's physics still works very well for everyday motion, but Einstein showed that space and time have a deeper structure. Classical thermodynamics describes heat and engines, but statistical physics explains heat in terms of particles and probability. The hot Big Bang model describes the expanding cooling universe, while inflation may explain why that universe began its observable history in such a smooth, flat and structured state. Science does not always replace old ideas. Sometimes it places them inside larger ones, like a smaller box inside a bigger box, and then politely asks whether anyone has seen the lid. There is also a human lesson here, or at least a sleepy one. The universe often appears simple from far away, then complicated up close, then simple again when seen from a deeper angle. The night sky looks like scattered stars. Telescopes reveal galaxies, nebulae, clusters, and cosmic expansion. Deeper study reveals a universe that was once hot, dense, and filled with ancient light. Still deeper study finds puzzles in that early state, and inflation offers a new simplicity beneath them. A small connected patch expanded rapidly. Smoothness became cosmic. Tiny fluctuations became structure. Curvature became nearly invisible. Unwanted relics were swept beyond reach. That does not make the story easy. It makes it coherent. And coherence is one of the things science seeks. Not just facts lined up like jars on a shelf, but connections between them. Inflation connects the large-scale appearance of the universe with its earliest physical conditions. It connects the cosmic microwave background with quantum fluctuations. It connects the absence of certain relics with the stretching of space. It connects the Big Bang model to a possible earlier phase of expansion. This is why cosmologists took inflation seriously. Not because it was a decorative addition, but because it addressed genuine tensions in the standard picture. It explained things that otherwise had to be assumed. It turned special initial conditions into the outcome of a physical process. It made the universe less like a strange coincidence and more like a story with an earlier paragraph. And as we sit with that thought, the Big Bang becomes less of a single beginning and more of a doorway. On one side is the familiar expanding universe, hot and bright in its youth, cooling into matter, atoms, stars, and galaxies. On the other side is the inflationary possibility, a brief but enormous stretching, driven by a field whose nature remains uncertain, setting the conditions for everything that followed. The doorway is not fully open. We cannot yet walk through and see every detail. But enough light comes through to suggest that the story before the hot Big Bang phase may be essential. So the bigger idea was needed because the universe was too smooth, too flat, too clean of certain relics, and too perfectly seeded with tiny variations for the simplest version of the hot Big Bang picture to explain on its own. Inflation gave scientists a way to understand these features as consequences rather than coincidences. It did not end the mystery of the origins, but it moved the mystery to a deeper and more precise place. Instead of simply asking why the early universe was so special, we can ask what physical process made it that way. That question leads naturally into the next part of the journey. If inflation is the answer to these puzzles, then we need to picture what actually happened during that rapid stretch. We need to think about space not as a still container, but as something that can expand with staggering intensity. We need to ask how fast can be when it is not objects moving through space, but the distances within space themselves growing. And this is where the story becomes both more concrete and more difficult to imagine, because the sudden stretch of inflation was not a blast, not a wave moving outward from a centre, not matter flying through darkness, but the fabric of the observable universe enlarging everywhere at once, carrying its tiny fluctuations with it as the small became vast. The fabric of the observable universe enlarging everywhere at once is not an easy thing to picture, because nearly every picture we carry around in daily life involves objects moving through space. A car moves along a road, a bird crosses the sky. A train leaves one station and arrives at another. Even when something expands, like steam spreading through a room or dough rising in a warm kitchen, we still imagine material pushing into an already existing space around it. Cosmic inflation asks us to change that habit. It asks us to imagine not things travelling through space, but space itself increasing the distances between things. The stage is not still while the actors move. The stage itself is growing, and growing so quickly that ordinary comparisons begin to creak under the weight. During inflation, the universe did not expand because galaxies were flying away from one another. Galaxies did not exist yet. Stars did not exist. Atoms did not exist. There were no glowing islands of matter rushing through a dark background. There was a hot and extremely early state dominated by fields and energy, and the geometry of space was changing at a tremendous rate. What would one day become the observable universe was being stretched from a tiny connected region into an enormous expanse. The important thing is that every part of that region was involved. There was no centre where inflation began, and no edge racing outward into emptiness. Every small patch of space became larger. Every distance increased. The stretching was built into space itself. This is why the phrase "faster than light" needs careful handling. It is often said that inflation expanded the universe faster than light, and in one sense that is a fair description. Distant regions could be carried apart from each other so quickly that the distance between them increased faster than a beam of light could cross it. But this does not break Einstein's rule that nothing can move through space faster than light. The rule applies to objects, signals, and information moving locally through space. Inflation was not a rocket ship breaking a speed limit. It was the expansion of space itself. No particle had to outrun light in its own neighbourhood. Instead, the distances between neighbourhoods grew at an astonishing rate. A simple way to picture this is to imagine two ants standing on a stretchy rubber sheet. The ants are not walking. They are simply standing there, perhaps discussing ant matters, which are probably important to ants. If the sheet stretches, the ants become farther apart even though neither ant has moved across the sheet. If the sheet stretches very quickly, the distance between the ants may grow faster than either ant could crawl. That does not mean the ants have broken their own speed limit. It means the sheet has changed beneath them. Inflation is something like that, except the sheet is not really a sheet, the ants are not really ants, and the universe, as usual, refuses to be as convenient as a classroom demonstration. The sudden stretch was also not like an explosion with debris flying outward. Explosions have centres, they happen at a location. They send material into surrounding space. If you stand far enough away, which is generally wise with explosions, you can watch the blast move through the environment. Inflation had no outside environment. Space itself was the thing changing. If there had been tiny rulers embedded in the early universe, the rulers would not have seen themselves flying through a room. They would have seen distant rulers becoming farther away because the space between them was growing. Nearby things would still behave normally in their immediate surroundings, but faraway regions would recede as the whole cosmic fabric expanded. This distinction is more than a technical detail. It helps explain how inflation could make the universe so large and so uniform without requiring a violent blast from a central point. The early patch that became our observable universe could have been small enough for its different parts to interact and settle into similar conditions. Then inflation stretched that patch so dramatically that those once neighbouring regions became separated by cosmic distances. The smoothness we see today is a memory of that earlier closeness. The stretch did not have to create uniformity from nothing. It preserved and enlarged the uniformity of a smaller region. The speed of the stretch is difficult to overstate without slipping into language that sounds exaggerated. But in inflation, exaggeration has to work rather hard to keep up. The expansion is usually described as exponential, which means that the size of the region did not simply increase by adding the same amount again and again. It multiplied again and again. A small patch grew larger, then that larger patch grew larger by the same factor, and then the result grew again and again and again. The process was brief, but repeated multiplication can do enormous things in very little time. Anyone who has ever agreed to receive a chain email from a relative knows that repeated multiplication can become alarming quickly. In ordinary expansion, we might imagine something growing steadily, like a balloon being inflated at a constant pace. Inflation was more extreme. The distance between 2 points could double, then double again, over and over in a tiny fraction of a second. That kind of growth can turn something unimaginably small into something enormous before there is time for anything familiar to happen. It is not that the universe was rushing in the way wind rushes or water rushes. It was that the scale of space was increasing with extraordinary intensity. This rapid growth did several important things at once. First, it smoothed the universe. Any initial irregularities in the patch were stretched out and diluted. Imagine a crumpled cloth being pulled tight. The little folds do not necessarily vanish from existence, but across the region you can see the surface appears smoother. Or imagine a tiny mark on a balloon. As the balloon inflates, the mark becomes spread over a larger area and its sharpness is softened. Inflation does something similar to the early universe. Features that might have made space uneven were pushed far apart and made less noticeable within our observable region. Second, inflation flattened space. If the early patch had any curvature, rapid stretching made that curvature harder and harder to detect locally. Again, Earth gives us a useful everyday clue. The whole planet is curved, but a small patch of ground appears flat to a person standing on it. If you enlarge a small region enough, its curvature becomes less obvious across the part you can measure. Inflation stretched the observable patch so much that its geometry became extremely close to flat. This helps explain why large-scale space today appears so geometrically balanced. Third, inflation diluted unwanted leftovers. Certain theories suggest that the early universe might have produced heavy exotic relics. Without inflation, those relics might have remained common enough for us to notice today. But if space expanded enormously after they formed, their density would have dropped dramatically. They would be spread so thinly that our observable universe might contain none at all. Inflation in this sense acts like a cosmic zooming out. Anything rare becomes far rarer. Anything localized becomes pushed beyond the horizon. The visible universe is left smoother, flatter, and cleaner. But inflation was not a perfect eraser, and that is fortunate. If it had removed every difference completely, the universe would have become too smooth to build anything interesting. The great success of inflation is that it can smooth the universe on large scales, while also creating the tiny variations that later become structure. That sounds contradictory at first, like tidying a room while carefully leaving just enough crumbs to build a city of biscuits, yet the physics allows it. The overall expansion smooths and flattens, while quantum fluctuations in the inflaton field and related fields are stretched to cosmic scales. The universe becomes mostly even, but not entirely. During the sudden stretch, the smallest fluctuations were carried outward by the expansion. These were not ordinary ripples moving through space like waves on a pond. They were quantum variations in fields, tiny differences in energy from place to place. Before inflation stretched them, they belonged to the microscopic realm. After stretching, they became spread across enormous distances. Once inflation ended, these variations remained as slight differences in density. Some regions were a little denser than average, others were a little less dense. Much later, gravity would notice. Gravity is not easily distracted. It would take those slight differences and slowly amplify them, pulling matter into denser regions and leaving emptier regions behind. This is one of the deepest ideas in the story. The sudden stretch did not merely make the universe bigger, it turned microscopic uncertainty into cosmic structure. The tiny fluctuations that quantum physics says should exist were enlarged until they became the first outlines of the cosmic web. The positions of galaxy clusters, the vast empty voids, and the broad pattern of matter across the universe may all trace back to fluctuations stretched during inflation, not in the sense that a particular galaxy was already planned in detail. There was no tiny sketch of the Milky Way waiting in the early universe, complete with a little arrow saying future home of confused mammals. Rather, there was a statistical pattern of slightly denser and less dense regions, and gravity later developed that pattern into structure. The sudden stretch also affected what parts of the universe could communicate with one another. Before inflation, the patch that became our observable universe could have been small enough for light and other influences to cross it. During inflation, that patch expanded so quickly that regions were carried outside each other's horizons. A horizon here means the limit of what can affect what within a given time. Once regions were stretched far enough apart, they could no longer exchange signals. They had once shared conditions, but after inflation they became separated by distances too vast for communication. Later, as the universe continued expanding more slowly and evolving, some regions came back within our observable reach, in the sense that their ancient light could eventually arrive. The cosmic microwave background is part of that recovered view, a record from a time long after inflation but still shaped by it. This horizon stretching is essential to inflation's power. It explains why distant parts of the sky look so similar. They did not become similar by talking across the universe after they were far apart. They were similar because they were once close together. Inflation stretched them apart after the similarity was established. It is a little like taking a small, evenly mixed batch of batter and spreading it across a very large tray. Later, someone looking at opposite corners of the tray might wonder how the batter there became so evenly mixed, since the corners are far apart. The answer is that the mixing happened before the spreading. As culinary cosmology goes, this one is not bad, though it does raise the question of whether the universe should be served with custard. The sudden stretch must also have ended. If inflation had continued in our region forever, the universe would have remained emptying and stretching in a way that would not lead to the hot particle-filled cosmos we know. Stars would not form if the energy driving inflation never changed into matter and radiation. So a complete inflationary story needs both the rapid expansion and a graceful exit from it. The field driving inflation had to shift from its high energy state into a different state, releasing energy into the particles and radiation of the hot early universe. That later stage is often called reheating, though it was not reheating in the ordinary sense of warming leftovers. It was the conversion of inflation's stored energy into the hot contents of the young universe. The details of that ending belong more fully to the next stage of the story, but they matter here because they show that inflation was a transition, not a permanent condition in our observable patch. For a brief interval, a special kind of energy dominated the behaviour of space. This energy did not dilute in the same ordinary way as matter or radiation during expansion. As a result, it could keep driving expansion strongly. Then the inflaton field changed, the rapid stretching slowed, and the universe entered the hot dense phase that the standard Big Bang model describes so well. Inflation prepared the conditions. The hot Big Bang evolution used them. This raises a natural question. What did it feel like during inflation? The honest answer is that there was nothing around to feel it. No atoms, no bodies, no clocks with hands, no observer drifting through the early universe with a clipboard and a mildly worried expression. But we can still ask what physical conditions would have been like. Space would have been expanding at a tremendous rate. Any particles or irregularities already present would have been diluted rapidly, quantum fields would have fluctuated. The energy of the inflaton field would have dominated the expansion. The universe would not have looked like a fiery explosion with sparks. In many models, inflation would have emptied and smoothed the patch, even as it stretched it, leaving behind the conditions for the hot universe only when inflation ended. That is another surprising feature. Inflation can make the universe colder and emptier while it is happening, because expansion dilutes ordinary particles and radiation. Yet when inflation ends, the energy driving it can be transformed into a hot bath of particles. so the universe can go through a phase of rapid smoothing and then become hot and filled with matter and radiation afterward. This helps explain why inflation is sometimes placed just before the hot Big Bang phase. It is not simply a hot fireball expanding from the beginning. It is a strange early period in which space expands dramatically under the influence of field energy, followed by the production of the hot contents that later evolve into the universe we can trace more directly. The faster-than-imagination quality of inflation comes partly from how quickly it changes the scale of everything, but it also comes from how completely it changes the meaning of distance. During inflation, 2 points that were once close could become so far separated that they would no longer share a common observable region. Space was not merely becoming larger, it was rearranging what could be connected to what. The visible universe we know may be only a small remnant of a much larger inflated region. Beyond what we can observe, there may be regions that were also stretched, perhaps with similar properties, perhaps not, depending on the deeper physics. The edge of what we see is not necessarily the edge of what exists. It is the edge of what light has had time to bring us. This is one reason inflation can make the universe feel both more understandable and more vast. It explains why our observable patch looks the way it does, but it also suggests that the whole reality may be much larger than what we can ever directly observe. Our cosmic horizon becomes less like a wall and more like the limit of a lantern in fog. There may be more beyond it, but the light from there has not reached us, and may never reach us if expansion keeps carrying regions apart. Inflation stretches not only space but also our sense of humility, which was already getting quite a workout. The sudden stretch also has consequences for time itself. During inflation, the expansion of space was so rapid that the usual sequence of events we imagine in a growing universe becomes compressed into an extraordinarily brief interval. Yet this brief interval could set conditions lasting billions of years. It created the broad uniformity of the cosmos. It laid down the density variations. It flattened the visible geometry. It pushed relics away. It shaped the starting point for later cosmic history. A tiny sliver of time, if our models are right, became one of the most important episodes the universe ever experienced. There is a useful caution here. Inflation is a theory with many versions and not every detail is known. When we say the universe stretched by an enormous amount, we are describing the broad mechanism shared by inflationary models, not a directly filmed event. We infer it from what it explains and from the patterns it predicts. The cosmic microwave background gives strong support to the idea that the early universe had the kind of fluctuations inflation naturally produces. The observed flatness of space fits inflation's expectations. The large-scale smoothness of the universe fits as well. But the exact engine of inflation, the identity and behavior of the inflaton field, and the details of how inflation began and ended remain active areas of study. The sudden stretch is a powerful explanation, but it is not a closed book. Still, as a physical picture, it is wonderfully coherent. Begin with a small connected patch of the early universe. Let it be dominated by a field whose energy causes space to expand at an accelerating rate. As space expands, the patch becomes enormous. Curvature is stretched away. Irregularities are smoothed. Rare relics are diluted. Quantum fluctuations are enlarged and frozen into large-scale density patterns. Then the field changes state, inflation ends, and its energy becomes the hot particles and radiation of the young universe. From there, the familiar cosmic story can proceed. Matter forms, light eventually travels freely. Gravity gathers the seeds into galaxies, and much later someone under a blanket wonders how the whole thing happened. The phrase frozen is sometimes used for the fluctuations, and it is useful if we handle it gently. During inflation, quantum fluctuations are stretched to such large scales that they stop behaving like tiny changing quantum ripples and become effectively fixed as classical variations in density. They are carried outside the horizon, unable to communicate across their full extent. Later, after inflation ends and the universe evolves, these variations re-enter the horizon and influence the motion of matter and radiation. This is part of how inflation connects early quantum behavior to later cosmic structure. A fluctuation begins as a small uncertainty, is stretched beyond causal contact, becomes a large-scale pattern, and eventually guides the growth of matter. This process is not visible directly, but it leaves signatures. The ancient microwave glow across the sky carries a pattern of slight temperature differences. Those differences correspond to early density variations. The pattern is not random in a casual sense, like crumbs scattered by a careless biscuit enthusiast. It has statistical properties that can be measured with great precision. Inflation predicts a pattern very much like the one we observe. That is one of the reasons cosmologists keep returning to the idea. The sudden stretch may sound extravagant, but it leaves behind a surprisingly disciplined fingerprint. It is worth noticing how different this is from the everyday idea of creation as a single dramatic blast. Inflation is subtle in its consequences, even though it is extreme in scale. It does not make galaxies immediately, it does not light stars, it does not build atoms, it prepares the conditions under which all those later things can happen. Its effects are written into geometry, smoothness, and tiny variations. It is less like watching a building rise and more like setting the foundations and slight ground contours that determine where rivers, roads, and cities might one day appear. The visible drama comes later. The crucial preparation happens early. And there is something calming about that in a way. The universe we see now, with all its brightness and structure, may owe its shape to a brief phase of expansion that left almost no direct objects behind. Inflation did not leave a monument floating in space with a plaque that reads this way to the beginning. It left patterns, it left the smoothness of the sky, it left the flatness of space, it left tiny differences that became everything uneven and interesting. To study inflation is to read the universe by inference, to look at the oldest light and the largest structures and reason backward toward an event too early to observe directly. The sudden stretch faster than imagination is therefore not merely a spectacle. It is an explanation for why the universe looks possible. A universe that expands too differently, curves too strongly, contains too many relics, or lacks the right small fluctuations might not produce galaxies like ours. Inflation gives the observable universe a plausible route from a tiny connected beginning to a vast structured cosmos. It takes the early state and makes it large without making it chaotic. It makes the universe uniform without making it empty of potential. It stretches the small, preserves the useful imperfections, and sets the stage for the long, slow work of gravity. As we move deeper into the mechanism, the next question becomes unavoidable. What kind of physical ingredient could drive such a stretch? Ordinary matter cannot do it. Radiation cannot do it in the required way. The expansion needs a special kind of energy, something that behaves less like particles flying around and more like a field-filling space with a persistent energy that pushes expansion into overdrive. This is where the inflaton field enters the story, not as a confirmed particle sitting neatly in a detector, but as the proposed hidden engine behind the earliest great growth of the cosmos. It is the part of the theory that tries to explain not only that space stretched, but why it stretched so dramatically in the first place, and how that stretching eventually gave way to the hot young universe from which everything familiar would slowly emerge. Ordinary matter cannot produce the kind of rapid expansion inflation requires. That is the first important clue. The matter we know, the matter that makes rocks, oceans, planets, and slightly too many cables behind a desk behaves in a way that slows expansion down. Gravity pulls, matter gathers, radiation thins out as space expands. If the early universe had been filled only with ordinary particles and light, expansion would still have happened, but it would not have surged into the extraordinary runaway stretching needed to solve the smoothness and flatness puzzles. Something else had to dominate the universe for that brief interval. something with unusual pressure, something that filled space almost evenly, something that could act less like a collection of particles flying about and more like an energy spread through space itself. This proposed something is called the inflaton field. The name is not especially elegant, but physics names are often practical rather than graceful. The inflaton is the hypothetical field thought to have powered cosmic inflation. It is not a field in the sense of a meadow with sheep in it, though a calm meadow with sheep would be a perfectly respectable thing to imagine at bedtime. In physics, a field is something that exists throughout space and can have a value at every location. The air temperature in a room can be thought of loosely as a field because every point in the room has a temperature. A magnetic field surrounds a magnet and can influence objects nearby. The gravitational field around Earth tells objects how to fall. Fields are not just decorations placed in space. In modern physics, they are often the most fundamental things we talk about. Particles themselves can be understood as little disturbances or excitations in underlying fields. The inflaton field, if it existed, would have filled the early universe. It would not have been a lump in one place or a machine sitting at the centre of reality. It would have been everywhere in the region undergoing inflation, with an energy that was nearly uniform from place to place. That uniformity matters. Inflation needs the universe to expand in a smooth, even way. If the engine were wildly different from one region to another, it would not naturally produce the large-scale smoothness we observe. The inflaton field is usually imagined as being in a special high-energy condition, one that does not immediately drain away. While it remained in that condition, its energy caused space to expand rapidly. The unusual feature of the inflaton field is not just that it had energy. Matter has energy. Radiation has energy. You have energy, though perhaps less of it late at night, and that is completely understandable. The key is how the energy of the inflaton field behaved as space expanded. Ordinary matter becomes more dilute when space grows. If you have particles spread through a volume and the volume becomes larger, the particles are farther apart. Their density drops. Radiation also loses energy as the universe expands because light waves are stretched, but the energy associated with the inflaton field could remain nearly constant as space expanded, at least for a short time. The field acted almost like an energy built into space itself. As more space appeared, the energy density did not quickly fade in the usual way. This kind of nearly constant energy density has a strange effect in general relativity. It creates a form of pressure that drives accelerated expansion. That can sound backwards, because pressure in everyday life usually pushes outward from inside something, like steam in a kettle or air in a balloon. But in cosmology, pressure and energy both contribute to how space evolves. A field with the right kind of pressure can make expansion speed up rather than slow down. During inflation, the inflaton field is thought to have created exactly that situation. Space did not merely continue expanding, it accelerated into a rapid stretch. A useful image is a ball resting on a landscape of hills and valleys. The height of the landscape represents the energy of the field. The position of the ball represents the state of the inflaton. If the ball is high on a gentle slope or sitting in a shallow high place, it has potential energy. As long as it stays there or rolls very slowly, that energy can drive inflation. The universe expands rapidly while the field changes only gradually. Eventually the ball rolls down toward a lower valley. When it does, inflation ends, and the stored energy is released into particles and radiation. This image is not perfect because the inflaton field is not really a ball, and its energy landscape is not a physical hill. But the picture helps. Inflation needs the field to remain in a high-energy state long enough for space to stretch enormously. If the field rushed downhill too quickly, inflation would end before it had solved the cosmic puzzles. If it stayed high forever, inflation would never end in our region, and the hot universe we know would not appear. The field had to behave in a rather particular way. It needed to linger, then change. It needed to drive the expansion, then give up its energy. It needed to be dramatic, but also know when to leave the stage. which is a quality not all dramatic things possess. This slow change of the inflaton field is often called slow rolling. We can describe it without any formulas. The idea is simply that the field moves gradually through its possible values, while its energy remains high enough to keep inflation going. During this time, the expansion of space is extremely rapid. Eventually, the field reaches a point where it can no longer maintain that special inflationary condition. It begins to oscillate or settle into a lower energy state. The energy that had been stored in the field is transferred into ordinary particles, radiation, and heat. This transition fills the universe with the hot contents that later become part of the standard Big Bang story. This ending process is often called reheating, though the name can be misleading. It was not a cold universe being warmed like soup on a stove. During inflation, ordinary particles and radiation would have been spread out and diluted until the universe became extremely empty in the usual particle sense. Then, when the inflaton field decayed or transferred its energy, space was filled with a hot bath of particles. It was as though the engine that had been stretching space suddenly converted its stored energy into the ingredients of the early universe. From that point onward, the universe could behave like the hot, dense, expanding cosmos described by the Big Bang model. This is why the inflaton field is sometimes called the hidden engine of inflation. It supplies the energy that makes space stretch so dramatically, and then it supplies the energy that becomes the hot early universe afterward. It does two jobs. First, it expands the stage, then it fills the stage with the material from which later cosmic history unfolds. Without a mechanism like this, inflation would be an effect without a cause, a grand stretch with no explanation for what powered it, or how it ended. But the inflaton field is still hypothetical. Scientists have not detected an inflaton particle in a laboratory. We do not know its exact identity. We do not know whether it is a completely new field, whether it is related to fields already known in particle physics, or whether inflation might be driven by something more complex than a single field. There are many models. Some use one inflaton field. Some use more than one field. Some connect inflation to high-energy physics beyond what has been directly tested. Others try to build inflation from ideas related to gravity itself. The broad picture is powerful, but the engine under the hood remains partly hidden. This is not unusual in physics. Often scientists infer the existence of something before they identify it directly. Neptune was predicted from its gravitational effects before it was observed. The neutrino was proposed to explain missing energy in nuclear processes before it was detected. Dark matter is inferred from its gravitational influence, though its particle identity remains unknown. The inflaton field is similar in spirit, though even more remote. It is proposed because it can explain the early universe's rapid expansion and the patterns we observe today. Its direct nature remains one of the open questions. One reason the inflaton is difficult to study is that inflation happened at energies far beyond anything we can easily recreate. Particle accelerators on Earth are extraordinary machines, but they cannot simply reproduce the full conditions of the earliest universe. They can give clues about high-energy physics, but the inflaton belongs to an era that may be far beyond our direct experimental reach. Instead, cosmologists search for its fingerprints in the sky. They study the cosmic microwave background, the distribution of galaxies, and possible patterns in primordial gravitational waves. The field itself is hidden, but its effects may be written into the large-scale structure of the universe. The most important fingerprints are the tiny fluctuations produced during inflation. If the inflaton field filled space, it would not have been perfectly smooth. Quantum physics does not allow fields to be completely still. Even in what seems like empty space, fields have small fluctuations. During inflation, these fluctuations were stretched enormously. Some regions ended up with the inflaton field slightly different from others. Those differences caused slight variations in how inflation ended and in how energy was distributed afterward. The result was a pattern of tiny density differences in the early universe. These density differences became the seeds of galaxies. That statement deserves a quiet pause, because it is one of the most remarkable claims in all of cosmology. The largest structures in the universe may have begun as tiny quantum fluctuations in the inflaton field, not as planned structures, not as little galaxy embryos with names and addresses, just tiny variations in energy, stretched by the expansion of space and later amplified by gravity. The inflaton field may have shaped not only the size and smoothness of the universe, but also the first pattern from which all later structure grew. This means the inflaton field had to be smooth enough to drive inflation evenly, but not so smooth that it erased all variation. It needed to be nearly uniform with small quantum fluctuations. The universe we see today reflects that balance. The cosmic microwave background is almost the same in every direction, but it contains tiny temperature differences. Those differences have exactly the kind of importance inflation gives them. They are small enough to preserve large-scale uniformity, but large enough to seed galaxies. The inflaton field, if this story is right, gave the universe both calm and texture. There is a gentle strangeness in that combination. Inflation is often described as a smoothing process, and it is. It stretches away curvature, dilutes relics, and makes the visible universe more uniform. But at the same time it magnifies microscopic quantum fluctuations. It smooths the broad fabric while preserving tiny threads of difference. Later, gravity pulls on those differences, and over billions of years they grow into the cosmic web. The universe becomes a mixture of order and variety. Too much order, and nothing forms. Too much disorder, and the cosmos becomes chaotic. The inflaton field may have helped set the balance. The field also has to explain why inflation stopped. This is not a minor detail. A theory of inflation that cannot end is not enough to explain our universe. During inflation, space expands so quickly that any ordinary matter becomes diluted. If the inflaton field continued driving accelerated expansion without changing, our region of the universe would never become the hot particle-filled place needed for stars and galaxies. So the field must eventually release its energy. In many models, it does this by rolling down its energy landscape and interacting with other fields, producing particles. These particles scatter, interact, and settle into a hot thermal state. The universe becomes filled with radiation and matter. The more familiar Big Bang evolution begins. That transition may have been complex. The inflaton field might not have simply poured its energy evenly into particles like water into a bowl. It may have oscillated, transferred energy in bursts, or interacted with other fields in ways that produce complicated patterns before everything settled. Some versions of the story include a phase before full reheating, where energy transfer is especially efficient and uneven. The details depend on the model, but the broad idea remains clear. Inflation ends when the inflaton field stops behaving like a source of sustained accelerated expansion and begins giving its energy to the contents of the universe. This also means that the hot Big Bang was not necessarily the absolute beginning. In this picture, the hot phase came after inflation. The heat of the early universe was produced by the decay or transformation of the inflaton field. That does not tell us what came before inflation. It does not explain why the inflaton field existed in the right state. It does not remove every mystery. But it gives a physical process that can connect an earlier inflationary era to the hot expanding universe we can study more directly. The question of how inflation began is especially difficult. For inflation to start, some region of the early universe must have had the inflaton field in the right kind of high-energy state, smooth enough over a large enough patch to drive accelerated expansion. Some models suggest that once inflation begins in a suitable patch, it naturally expands that patch so much that it dominates what becomes observable. Other models try to explain the initial conditions through deeper physics, but this remains one of the areas where cosmologists are careful. Inflation explains many observed features if it occurs, but why it occurred in the first place is still an open question. There is also the possibility that inflation may not end everywhere at once. In some models, inflation ends in certain regions while continuing in others. our observable universe would be inside a region where inflation ended, reheating occurred, and the familiar cosmic evolution began. Elsewhere, inflation might continue, producing more regions where it eventually ends. This idea is known as eternal inflation. It is fascinating, but also speculative and difficult to test. It suggests a cosmos much larger than what we can observe, perhaps with many bubble-like regions, each with its own hot Big Bang phase. Whether this is a real feature of nature or a consequence of certain mathematical models remains unsettled. Even without going that far, the inflaton field already stretches the imagination. A single field, nearly uniform across an early patch of space, may have driven the fastest expansion in cosmic history, generated the seeds of structure, and then transformed into the hot contents of the young universe. It is an economical idea, though not a simple one. It gives one physical ingredient several connected roles. It explains why inflation happens, how fluctuations arise, and how the universe becomes hot afterward. That is part of its appeal. The hidden engine does not merely push space outward, it links the earliest expansion to the later universe. To make the idea more grounded, it may help to compare the inflaton field with another field we know exists, the Higgs field. The Higgs field fills space and gives certain particles mass through their interaction with it. Its associated particle, the Higgs boson, was discovered in a particle accelerator. The inflaton field may be somewhat similar in the broad sense that it is a field filling space with important physical effects, but it is not the same thing in the standard inflationary picture, and no inflaton particle has been found. Some researchers have explored whether the Higgs field itself could be connected to inflation, but that is a specific kind of model, not a settled fact. The safer statement is that the inflaton field is a proposed field, still unidentified, introduced to explain cosmic inflation. This is a good example of how physics combines imagination and restraint. The idea is imaginative because it asks us to picture a field driving the expansion of space itself. It is restrained because it must answer to observation. The field cannot have just any properties. It must produce enough inflation to solve the horizon and flatness problems. It must create density fluctuations with the pattern seen in the cosmic microwave background. It must end in a way that produces a hot universe. It must not create features that observations have already ruled out. Each new measurement narrows the possibilities. The cosmic microwave background is especially important because it preserves a record of early density variations. If those variations came from the inflaton field, then their pattern tells us something about the field's behaviour. The variations are nearly scale balanced, meaning they appear with similar strength across a wide range of sizes, though not exactly identical. They are also very close to the kind of random pattern expected from quantum fluctuations stretched by inflation. These observations do not reveal the inflaton directly, but they constrain its possible energy landscape and how it changed during inflation. Scientists also search for a particular kind of signal from inflation in the polarization of the cosmic microwave background. Polarization is a property of light related to the direction in which its electric field vibrates, though we do not need to dwell on the technical detail. Some inflationary models predict that the rapid expansion would have produced primordial gravitational waves, ripples in space itself from the earliest universe. These waves could leave a faint swirling pattern in the microwave background's polarization. Detecting such a signal would be a major clue about inflation and the energy scale at which it occurred. So far, the search continues, and the limits keep improving. The absence of a detected signal at certain levels has already ruled out some simpler models. This is the quiet work of cosmology. The theory imagines an invisible field in the earliest universe. Observations of ancient light test what that field could have been like. Models are proposed, compared, adjusted, or discarded. The universe does not answer in ordinary sentences. It answers in faint patterns across the sky, tiny temperature differences, subtle polarization signals, galaxy distributions, and the stubborn silence where certain signals are not found. Scientists learn to read both the marks and the missing marks. The inflaton field also reminds us that empty space is not necessarily empty. In everyday language, empty means nothing is there. In physics, a region with no particles can still contain fields, energy, and structure. During inflation, the energy of a field-filling space may have dominated everything. This is deeply different from the way we normally think about reality. We're used to objects being important and the space between them being passive. Inflation reverses that instinct. The space-filling field is the main actor. The later objects are consequences. There is something almost restful in that idea, though it is also strange. Before the universe became crowded with galaxies and stars, before matter clumped and burned and formed worlds, there may have been a simpler state dominated by one nearly uniform field. A field quietly holding energy. A field changing slowly. A field whose pressure made space expand faster and faster. It was not quiet in the human sense because there was no sound, no air, and no listener. But compared with the later universe full of collapsing gas clouds, exploding stars and planets developing weather systems with opinions, inflation has a kind of mathematical stillness. The field is nearly smooth. Space stretches. Quantum fluctuations whisper underneath. Those whispers, of course, become very important. The inflaton field is not only the engine of expansion, it is also the source of the ripples. The same field that smooths the universe also carries the tiny variations that prevent it from becoming featureless. The dual role is one of the most elegant parts of the theory. The inflaton does not need to plant structure separately. Its quantum nature provides the seeds automatically. During the rapid stretch, fluctuations that would normally remain microscopic become cosmic. When inflation ends, the energy of the field becomes the hot contents of the universe, and the stretch fluctuations become density variations within that contents. After a heating, the inflaton field no longer dominates our region. It has done its work, at least in the standard picture. The universe is now filled with particles and radiation. Expansion continues, but no longer in the same explosive inflationary way. Gravity begins its long, slow influence on the tiny density variations. Radiation streams through the hot plasma. Matter gradually becomes more important. Eventually atoms form and light decouples, creating the cosmic microwave background. Much later, the first stars ignite. All of that later history depends on the conditions left behind when the inflaton field released its energy. So the hidden engine is hidden in more than one sense. It is hidden because we have not directly detected it. It is hidden because it acted before the earliest light we can observe. It is hidden because its presence must be inferred from patterns rather than seen directly. And it is hidden because, if it worked as expected, it transformed itself. The energy of the inflaton field did not remain sitting around as an obvious relic. It became the hot early universe. It vanished into the world it helped create, rather like a cook who prepares a meal, washes every pan, turns off the kitchen light, and leaves only the dinner behind. Still, the dinner contains clues. The cosmic microwave background tells us about the density variations. The large-scale distribution of galaxies tells us how those variations grew. The flatness of space tells us about the stretching. The absence of certain relics tells us about dilution. Piece by piece, the hidden engine is reconstructed from what it left behind. This is not easy, but it is one of the reasons cosmology is so compelling. We are trying to infer a field from the shape of the universe. As we follow the inflaton field through this early story, the next natural step is to look more closely at those quantum fluctuations. They begin as tiny variations in a field. Inflation stretches them beyond microscopic scales. They become density differences. Later, they appear as faint temperature patterns in the oldest light and as the seeds of galaxies. This is where the universe turns the smallest possible disturbances into the largest visible structures, and where the hidden engine of inflation becomes not just a driver of expansion, but the source of the first ripples written across the sky. Those first ripples are among the most delicate clues the universe has ever left for us. They are not ripples in the ordinary sense, not waves lapping at a shore or rings spreading across a pond after a pebble drops in. There was no pond, no shore, no pebble, and certainly no small cosmic child crouched nearby thinking, I wonder what happens if I throw this in. The ripples we're talking about were fluctuations in fields, tiny variations in energy from one place to another, born in the strange rules of quantum physics, and then stretched by inflation until they became part of the large-scale pattern of the cosmos. This is one of the most astonishing ideas in modern cosmology. The universe around us, with its galaxies, clusters, vast empty regions, glowing nebulae, and long filaments of matter, may have begun as the amplified trace of quantum uncertainty. That is a quiet sentence, but it carries an enormous amount of weight. It means that the grand structure of the universe may have roots in the smallest restless behaviour of nature. The tiny and the immense are not separate stories. They are connected by the sudden stretching of space during inflation. To understand this gently, it helps to return to the inflaton field. During inflation, the inflaton field was not perfectly uniform, even if it was smooth enough to drive expansion in a steady way. Quantum physics tells us that fields cannot be completely still. Even in what we might call empty space, there are fluctuations. This does not mean little particles are popping like bubbles in a cartoon. The real physics is subtler than that. It means that the value of a field and the energy associated with it cannot be perfectly fixed everywhere with absolute calm. There is always a tiny uncertainty, a small trembling built into the foundation of the physical world. In everyday life, these quantum tremblings are hidden from us. Tables do not shimmer into different positions while we eat dinner, which is useful, especially if soup is involved. The world appears stable because huge numbers of particles and fields average out into predictable behaviour. But in the early universe, during inflation, the situation was different. The expansion of space could take microscopic fluctuations and stretch them to enormous sizes. A fluctuation that began far smaller than an atom could be pulled outward until it covered a region much larger than any ordinary physical object. With enough stretching, the quantum world left marks on the cosmic sky. This is where inflation becomes more than a way to smooth the universe. It becomes a way to write information into it. The inflaton field fluctuated slightly from place to place. Some regions had just a little more energy, others had just a little less. These differences affected the density of the universe after inflation ended. When the inflaton field released its energy into particles and radiation, the tiny variations became tiny differences in how much stuff there was from one region to another. Most places were nearly the same, but not exactly. The universe was born from inflation with a soft grain to it, like very fine texture in paper. That texture mattered enormously. Gravity is sensitive to differences. A region that is slightly denser than its surroundings pulls a little more strongly. It draws in more matter. As it gains matter, its gravity strengthens, and it draws in still more. This is a slow process, not a sudden one. The early universe did not immediately form galaxies the moment inflation ended. It took a long time for those small differences to grow. Radiation, matter, expansion, and gravity all interacted in a complex cosmic balance. But the beginning of structure was there. The seeds had been planted. If inflation had left the universe perfectly smooth, gravity would have had no preferred places to gather matter. Every region would pull equally in every direction. The cosmos would remain a bland mist, expanding and cooling without forming stars or galaxies. It might be mathematically tidy, but it would not be hospitable to complexity. On the other hand, if the early universe had been too uneven, matter might have collapsed too quickly or too violently, producing a very different cosmos. What we observe is a universe with just enough variation. It is smooth on large scales but lightly rippled. Inflation gives a natural way to produce that balance. The ripples are visible to us most clearly in the cosmic microwave background, the ancient afterglow released when the universe became cool enough for light to travel freely. This happened long after inflation, but the pattern in that light carries information from much earlier times. The The cosmic microwave background is almost perfectly uniform, which tells us the early universe was extraordinarily smooth. But when scientists measure it with great precision, they find tiny temperature differences across the sky. Some spots are slightly warmer, some are slightly cooler. These differences are incredibly small, but they are not noise. They're a map of the early density variations that later grew into structure. Imagine looking at a calm lake at dawn. From a distance, the surface seems smooth, reflecting the sky in soft silence. But if you look carefully, you notice tiny ripples. They reveal something about the breeze, the water, perhaps a fish moving below. The cosmic microwave background is something like that. It looks nearly uniform at first, but its tiny variations reveal the early universe's hidden motion and structure. The difference, of course, is that this lake covers the sky. The dawn happened billions of years ago, and the ripples may have begun as quantum fluctuations during inflation. Apart from that, quite ordinary. These tiny temperature patterns are not random in the careless sense. They have a statistical form. Scientists can study how strong the variations are on different size scales, how they are distributed, and whether they match the predictions of inflation. One of inflation's important successes is that it predicts fluctuations that are nearly the same strength across a wide range of scales, but not exactly the same. Observations show a pattern very close to this. The match is not a decorative detail. It is one of the reasons inflation became such a central idea in cosmology. The word nearly matters. If the pattern were exactly the same on every scale, that would suggest one kind of idealized behavior. But the measured universe shows a slight tilt, a gentle difference in the strength of fluctuations depending on their size. Many inflationary models naturally predict such a slight tilt, because the inflaton field changes slowly while inflation proceeds. Fluctuations created earlier and later during inflation can have slightly different strengths. That subtle difference becomes part of the pattern we observe in the oldest light. In this way, the cosmic microwave background is not just a picture. It is a record of how the inflationary engine may have changed while it was running. There is another important feature. The fluctuations appear to be very close to Gaussian, a word from statistics that describes a familiar bell-shaped kind of randomness. We do not need the technical details to appreciate the meaning. It suggests that the fluctuations behave like the natural random variations expected from simple quantum processes stretched by inflation. If the pattern had been strongly non-Gaussian, with unusual correlations or lopsided behavior, it might point to more complicated physics. Scientists search for these deviations carefully, because they could reveal whether inflation involved one field, several fields, or something stranger. So far, the simplest broad picture remains strongly supported, though not every detail is settled. The ripples also appear to be adiabatic, another technical word that can be explained calmly. It means the variations affected the overall density of the early universe in a coordinated way, rather than creating completely separate changes in different ingredients. Matter, radiation, and other components varied together in the pattern expected if the ripples came from fluctuations in the main field that set the timing and energy of reheating. This again fits well with many inflationary models. The universe seems to have received its early texture from a common source, not from a messy collection of unrelated disturbances. These clues make the sky feel like a manuscript, not one written in letters, but in temperature differences, polarization patterns, galaxy positions, and the faint statistical character of ancient light. Cosmologists read this manuscript with instruments and computers, but the basic idea is simple enough to hold in the mind. The early universe was not perfectly even. Its tiny unevenness had a pattern. That pattern looks like what inflation would create by stretching quantum fluctuations. Later, gravity turned the unevenness into the universe we see. The process from quantum ripple to galaxy is long and patient. After inflation ended and the universe became hot, matter and radiation formed a dense plasma. Light could not yet travel freely because it kept scattering off charged particles. The universe was like a glowing fog. The density ripples influenced this plasma. In denser regions, gravity tried to pull matter inward. Radiation pressure pushed back. This created waves in the early plasma, enormous sound like oscillations moving through the young universe. These waves left their own imprint in the cosmic microwave background, a pattern of preferred sizes in the temperature variations. Eventually the universe cooled enough for electrons and nuclei to combine into neutral atoms. Once that happened, light could move freely. The cosmic microwave background was released, carrying a snapshot of the ripples at that time. The matter, no longer pushed around so strongly by light, continued responding to gravity. Dark matter, which had already been gathering under gravity, helped shape the growing structure. Over hundreds of millions of years, denser regions drew in gas. The first stars formed. Galaxies assembled. Clusters grew. The tiny quantum ripples had become the first large-scale instructions for cosmic architecture. This does not mean every detail of the present universe was predetermined. The exact history of galaxy formation is complex. Collisions, feedback from stars and black holes, gas cooling, dark matter halos, and countless local processes shape the final outcome. The early ripples gave broad starting conditions. They created the initial pattern of slightly denser and slightly emptier regions. Later cosmic history developed that pattern in rich and complicated ways. It is a little like the grain of wood influencing how a carving turns out. The artist, tools, and time matter too, but the original grain quietly guides what is possible. One of the loveliest things about this story is that the ripples are still visible in more than one way. We see them in the cosmic microwave background as tiny temperature differences. We see their later growth in the distribution of galaxies. Galaxies are not scattered randomly like salt thrown impatiently across a table. They form a cosmic web, with long filaments, dense knots, and vast voids. This web reflects the growth of early density variations under gravity. By comparing the microwave background with galaxy surveys, scientists can test the same underlying story across different eras of cosmic history. The ancient light shows the seeds, the galaxy distribution shows the grown forest. The quantum origin of those seeds is what makes inflation so extraordinary. In most areas of life, quantum effects are hidden deep below ordinary experience. They belong to laboratories, particle detectors, atoms, and the fine structure of matter. Inflation brings them into the open on the largest possible stage. It says that quantum fluctuations were not merely small curiosities. They were stretched until they became the foundation of cosmic structure. Without inflation, such microscopic fluctuations would remain microscopic. With inflation, they become written across the sky. There is a small danger here of making quantum fluctuations sound too much like little specks that simply got enlarged, like dust under a microscope. That image is useful only up to a point. Quantum fluctuations are not tiny objects. They are variations in fields described by quantum rules. During inflation, these variations were stretched beyond the horizon, meaning regions within a single fluctuation could no longer communicate with each other. Once stretched, they became effectively classical in their behavior. That means they could act like real density variations in the universe, rather than remaining purely quantum uncertainties. The transition from quantum possibility to classical pattern is subtle, and still discussed in foundations of physics, but the cosmological effect is clear. The fluctuations became the initial unevenness that later structure needed. The horizon is important again. While a fluctuation is smaller than the horizon, causal processes can act across it. During inflation, expansion stretches fluctuations so quickly that they grow larger than the horizon. Once that happens, they are frozen in a certain sense. They no longer oscillate in the same way. They are carried along as large-scale patterns. After inflation ends, the horizon grows in relation to these scales, and the fluctuations eventually come back inside causal contact. Then they can influence matter and radiation in ordinary ways. This leaving and re-entering of the horizon is part of the reason the inflationary mechanism produces such a clean and measurable pattern. The sky, therefore, contains information about different moments during inflation. Fluctuations on very large scales left the horizon earlier. Fluctuations on smaller scales left later. By measuring the strength of variations across different scales, scientists can infer how the inflationary field behaved over time. This is delicate work. The cosmic microwave background is like a fossil, but not a fossil of bones. It is a fossil of conditions, a preserved pattern from the young universe. Reading it requires careful instruments, precise models, and a willingness to argue politely for many years about systematic errors. Polarization adds another layer to the story. The ancient light of the cosmic microwave background is not only slightly warmer or cooler in different directions, it is also polarized in faint patterns. These patterns arise from the scattering of light in the early universe and from the distribution of density variations. Some polarization patterns are expected from the ordinary scalar fluctuations, the density ripples we have been discussing. Another type of pattern could be produced by primordial gravitational waves from inflation. These gravitational waves would be ripples in space itself, generated during the rapid expansion. Detecting their imprint would open a new window onto inflation and the energy scale at which it happened. So far, the search for this primordial gravitational wave signal continues. There have been exciting moments, careful reanalysis, and reminders that dust in our own galaxy can imitate some of the patterns scientists are looking for. The universe, in addition to being vast and mysterious, is also inconveniently dusty. But even non-detections are useful. They rule out some inflationary models and guide theorists toward others. Every improvement in measurement gives a sharper view of what inflation could have been. The quantum ripples also teach us something about randomness and structure. The early fluctuations were random in the quantum sense, yet from that randomness came organized cosmic form. This is not a contradiction. Random initial variations can grow under consistent physical laws into complex patterns. Snowflakes, clouds, coastlines, and living systems all show how simple rules and initial variations can produce rich structure. In the universe, gravity acts as the great amplifier. It takes tiny density differences and magnifies them over time. The randomness gives variety. The laws give shape. There is a quiet humility in realizing that our galaxy may owe its existence to a fluctuation with no special intention behind it. A slightly denser region in the early universe helped matter gather. That matter eventually became part of galaxies. In one galaxy, around one ordinary star, a planet formed. On that planet, chemistry became biology. Biology became awareness, and awareness became someone asking what happened during cosmic inflation. The path from quantum ripple to question is long, indirect, and full of contingencies. But the connection is real enough to be moving. We are made possible by the universe's earliest tiny unevenness. At the same time, it is important not to overstate what inflation explains. It explains the origin of the initial density variations in a broad and successful way, but it does not explain every detail of cosmic structure by itself. Dark matter plays a crucial role in the growth of galaxies. Ordinary matter interacts with radiation, cools, heats, collapses, and forms stars. Dark energy affects the later expansion of the universe. The story from first ripple to present cosmos involves many ingredients. Inflation provides the seeds and the early pattern, but the universe spends billions of years gardening. The cosmic microwave background remains the cleanest early record because it comes from a time before stars and galaxies complicated the view. It shows the ripples while they were still small and relatively simple. Later, the universe becomes messy in wonderful ways. Stars explode, black holes grow, galaxies merge, gas heats and cools, and everything becomes more difficult to reconstruct. The ancient light is therefore precious. It is a baby picture of structure before structure fully grew up. Like many baby pictures, it is slightly blurry, but very meaningful to those who know what to look for. When scientists create maps of the cosmic microwave background, they are mapping differences so tiny that the whole sky would seem almost the same temperature without sensitive instruments. Yet those tiny differences contain a treasure of information. They tell us about the age, composition, geometry, and early conditions of the universe. They tell us how much ordinary matter and dark matter were present. They support the idea that space is very close to flat. They reveal the pattern of primordial fluctuations, and through that pattern, they give us one of our best clues about inflation. This is why the phrase written across the sky is more than a pretty image. The ripples really are written there, not in ink but in light. The oldest light carries a temperature pattern. The distribution of galaxies carries a matter pattern. The two are connected. They're different pages of the same cosmic record. Inflation, if correct, is the event that took quantum fluctuations and enlarged them until they could be recorded on those pages. There is also a pleasing reversal in this story. We often think of the sky as distant and separate from the microscopic world. Telescopes look outward. Particle physics looks inward. Cosmology tells us that outward and inward meet. To understand the larger scales, we need quantum physics. To understand the smallest fluctuations, we need the expansion of the entire universe. The sky becomes a kind of magnifying glass for the quantum world. Inflation stretched microscopic behavior until it became visible across billions of light years. This does not make the universe less mysterious. If anything, it makes the mystery more precise. We can ask what kind of field produced the fluctuations. We can ask whether there were multiple fields. We can ask whether the fluctuations were exactly as simple as the basic models suggest. We can ask whether primordial gravitational waves exist at a level we might detect. We can ask whether the inflaton field was related to known physics, or belonged to a deeper layer not yet reached by experiments. These are not vague questions. They are questions with observational consequences, and that is what makes them scientifically alive. The ripples also remind us that the early universe was not a perfect blank. It had history even before the oldest light we see. The cosmic microwave background is often described as the earliest visible surface, but it is not the beginning. It is a later record shaped by earlier processes. Inflation, reheating, particle interactions, and the growth of fluctuations all happened before that light was released. When we look at the microwave sky, we are seeing a message from a young universe, but the message includes echoes of an even younger one. The handwriting began before the page became visible. As the night settles and the mind softens around these ideas, it may help to hold the whole sequence simply. Quantum fields fluctuate. Inflation stretches those fluctuations enormously. The inflaton field eventually releases its energy, filling the universe with hot matter and radiation. The stretched fluctuations become tiny density differences. The early plasma responds to those differences, leaving patterns in the oldest light. Gravity later amplifies the density differences into galaxies in the cosmic web. The largest structures we can map today began as the smallest variations nature permits. That is the remarkable bridge, from uncertainty to structure. From field fluctuations to galaxies. From the earliest stretch of space to the patterned sky. The universe did not need someone to place galaxies by hand. It needed laws, fields, expansion, gravity, and time. Given those, tiny ripples could grow into the architecture of everything we see. And once those ripples were stretched across the young universe, they did more than seed galaxies. They also helped reveal how inflation solved the larger puzzles of smoothness and flatness. The same rapid expansion that magnified quantum fluctuations also made the observable universe so even and geometrically balanced. To see that more clearly, we need to look at the broader effect of inflation on the shape and texture of space itself, because the ripples were written on a canvas that inflation had already stretched almost impossibly wide, smoothing its wrinkles, flattening its curves, and leaving the young cosmos ready for the slow work of gravity. The canvas that inflation stretched was not empty in the simple sense, and it was not smooth in the perfect sense. It was a physical universe, filled with fields, energy, and tiny quantum variations. But compared with what came later, it was astonishingly even. The question is how it became that way on such enormous scales. Why should the distant sky look so similar from one direction to another? Why should the large-scale geometry of space look so balanced? Why should the universe be calm enough for galaxies to form over time, rather than wildly distorted from the beginning? Inflation answers these questions by doing something almost absurdly simple in idea, though extreme in practice. It stretches. Stretching is a familiar action, but cosmic stretching is not familiar at all. When you smooth a bedsheet, you pull the fabric outward, and small wrinkles become less noticeable. When you inflate a balloon, marks drawn close together move apart, and the surface of any small patch begins to look flatter. When dough rises, raisins embedded in it separate as the dough expands. These examples are not exact, because the universe is not a bedsheet, a balloon, or a loaf of bread, though a loaf of bread is admittedly easier to understand after midnight. But each example gives a useful hint. Expansion can dilute irregularities. It can make curves less obvious. It can take a small region and make it large while preserving its broad character. Before inflation, the patch of the early universe that would become everything we can observe may have been tiny enough for its different parts to influence one another. Light energy and fields could interact across it. Conditions could even out. Temperature differences could be smoothed. It is much easier to understand why a small connected region has a nearly uniform temperature than why opposite sides of the present observable universe do. In a small room, heat can spread from one side to the other. In a sealed collection of separate rooms, it cannot. The mystery of the oldest light is that the far separated regions of the sky look as though they once shared a common thermal history. Inflation says they did. They were once close. They were brought into similarity before the great stretch carried them far apart. This is the heart of the smoothness problem. The cosmic microwave background, the ancient glow left from the time when light first travelled freely, is almost the same temperature in every direction. Not exactly the same, because the tiny differences are very important, but nearly the same to an astonishing degree. Without inflation, the standard hot expanding universe struggles to explain this. Regions now seen on opposite sides of the sky should not have had enough time to exchange signals before that glow was released. They should not have been able to coordinate their temperatures, yet they appear to match beautifully. Inflation solves this by changing the history of those regions. They were not always distant strangers. They began as neighbours within a small connected patch. They had time to share conditions. Then inflation expanded that patch so rapidly that the regions were pushed far beyond one another's reach. Later, when the universe slowed into its more ordinary expansion and eventually released the cosmic microwave background, those regions still carried the memory of their early shared state. They looked similar because their similarity had been established before inflation separated them. The universe did not need to send messages across impossible distances afterward. The message had already been received before the walls moved apart. This is why inflation can make the cosmos smooth without requiring a miracle of coordination. It takes a local smoothness and enlarges it. Imagine beginning with a small patch of fabric that is fairly even. If you stretch it enormously, the visible section can become vast and still appear even. The stretching does not need to decide the fabric should be smooth everywhere. It only needs to take one smooth enough patch and make it into the region we can see. In cosmology, this is powerful because our observable universe does not have to represent the entire universe. It may be only a portion of a much larger reality. Inflation can make one originally small region large enough to contain everything within our cosmic horizon. The word horizon here is useful, but it can be misleading if we picture a sharp physical wall. A cosmic horizon is not a brick boundary at the edge of space. It is a limit set by time, light, and expansion. It marks how far information could have travelled. During inflation, space expanded so rapidly that regions were carried beyond each other's ability to communicate. What had been connected became disconnected. This sounds odd, but it is central to the explanation. Inflation first allows similarity to arise in a small region, then stretches that similarity across enormous distances, creating a universe that looks uniform even where communication later becomes impossible. The same stretching also makes the universe flat, or at least makes our observable region appear very close to flat. Flatness in cosmology does not mean the universe is like a thin tabletop. It means the geometry of space behaves, on large scales, very much like the familiar geometry we learn from ordinary experience. In a flat space, the rules of distance and angles follow the simple patterns we expect. In a curved space, those rules change over large distances. The universe could have had strong positive curvature or strong negative curvature. It could have been shaped in a way that made its large-scale geometry very different from what we observe, but measurements show that the visible universe is extremely close to flat. Without inflation, this near flatness looks strangely precise. In the early hot Big Bang picture alone, the universe would have needed to begin with a very particular balance in order to look so flat today. A small early departure from flatness would have grown more noticeable over time. The fact that the universe remains so close to flat would seem to require an extraordinary adjustment at the beginning. Inflation offers a natural way out. Stretch space enough, and any curvature in the original patch becomes harder and harder to detect. Think about Earth again. Its surface is curved, but if you stand in a field and look around, the ground appears flat. The curvature is real, but it is spread across a scale much larger than your immediate view. If you could enlarge a small patch of a curved surface until it became enormous, the local curvature would become less obvious within that patch. Inflation does this to the observable universe. A region that may have had curvature before inflation is stretched so much that, across the part we can see, it appears nearly flat. The curve has not necessarily been erased from all existence. It has been pushed beyond the scale of our observable patch. This is one of the reasons inflation feels so elegant. Smoothness and flatness come from the same basic action. Stretching a small connected region makes it look uniform across great distances. Stretching it also makes its geometry look flat. The theory does not need one explanation for temperature and another unrelated explanation for geometry. The rapid expansion handles both. It turns a special-looking universe into the natural result of a physical process. But there is a subtle point here. Inflation does not make everything exactly smooth and exactly flat in the strictest possible sense. Observations do not require that, and the universe itself does not seem to be perfectly featureless. Instead, inflation makes the observable universe smooth and flat enough. Enough for the cosmic microwave background to have nearly the same temperature in all directions. Enough for large-scale space to behave as though it has almost no curvature. Enough for the universe to evolve in a stable way, but it also leaves room for tiny variations. Those variations are essential. They are the seeds of galaxies, clusters, and all the structure that later forms. So inflation performs a kind of balancing act. It smooths away large irregularities, but it does not wipe out the small quantum fluctuations. In fact, it stretches those fluctuations and turns them into the initial density pattern of the universe. The result is a cosmos that is calm on large scales and gently uneven on smaller ones. This is exactly the kind of universe we observe. Look broadly, and the universe appears homogeneous and isotropic, which means it looks much the same from place to place and in every direction when averaged over enormous scales. Look more closely, and it is full of galaxies, voids, filaments, and clusters. Inflation helps explain how both can be true. This difference between large-scale smoothness and local structure is important. The universe is not smooth if you look at a galaxy. A galaxy is dense, bright, and filled with stars. It is very different from an empty cosmic void. But if you average over immense distances, these differences begin to blend into a larger pattern that is remarkably uniform. It is a little like looking at a piece of fabric. Up close, you see threads, knots, and tiny imperfections. From far away, it appears smooth. Inflation explains why the faraway view is so even, while quantum fluctuations explain why the close-up view is not blank. The smoothing also affects any earlier disturbances. Suppose the pre-inflationary patch contained irregular waves, lumps, or relics. Rapid expansion would stretch their wavelengths, dilute their density, and push many of them far outside the observable region. Anything that varied sharply across small distances could be spread over enormous scales. Anything rare would become rarer within the region we can see. In this sense, inflation acts like a cosmic reset. It does not erase the laws of physics or make the universe empty forever, but it clears away many troublesome initial features that would otherwise remain visible. This helps with another old worry in cosmology. Some high-energy theories predicted that the early universe might produce exotic heavy relics, such as magnetic monopoles or other defects. These would be unusual objects, leftovers from changes in the state of fields as the universe cooled. If too many existed, they might dominate the universe or be detectable today. Yet we do not see them in the expected abundance. Inflation provides a simple explanation. If they formed before or during the early phase of inflation, the rapid expansion would spread them out so drastically that our observable universe might contain none. They would not be destroyed necessarily. They would be carried beyond our horizon or diluted to near invisibility. That is another way inflation makes the cosmos cleaner. It does not merely smooth temperature, it reduces the concentration of unwanted relics and stretches away complicated initial features. This does not mean the universe becomes empty in the final sense, because inflation eventually ends and reheating fills space with particles and radiation. But during inflation itself, ordinary matter and radiation are diluted. The inflaton field remains the dominant energy source. Then, when inflation ends, that field transfers its energy into the hot contents of the young universe. The cleaned and stretched stage becomes filled again, but now with the right kind of initial conditions for the standard Big Bang evolution. This sequence can feel strange because inflation both empties and fills the universe, depending on which part of the process we mean. During the rapid stretch, ordinary particles are spread thin. Space becomes dominated by the nearly uniform energy of the inflaton field. Afterward, when the field decays, its energy becomes a hot bath of particles. The universe is reheated and enters the familiar hot expanding phase. So inflation first makes the observable region smooth, flat, and nearly empty of old clutter. Then it ends by providing the energy for matter and radiation. It is rather like clearing a room, polishing the floor, and then immediately holding the loudest dinner party in cosmic history. The flatness produced by inflation also explains why the universe could continue expanding for so long without quickly recollapsing or flying apart in a very different way. In the simplest terms, a universe with too much positive curvature might eventually stop expanding and collapse, while one with too much negative curvature might become increasingly open and dilute. Our universe sits remarkably close to the boundary between these possibilities. Inflation drives the visible patch toward that boundary. It makes the balance less mysterious by turning it into an attractor, a condition the expansion naturally approaches in the observable region. Again, the exact details depend on the model, but the general idea is strong. Accelerated expansion makes the contribution of curvature less important relative to the dominant energy of the inflaton field. By the time inflation ends, curvature has become negligible across the part of the universe we can see. Later expansion preserves this near flatness in a way that matches observations. What once looked like a delicate initial adjustment becomes the natural consequence of a rapid early stretching. This is one reason cosmologists often describe inflation as setting the initial conditions for the hot Big Bang. It takes a small patch and prepares it. It explains why the patch is smooth enough, flat enough, and free enough of certain relics. Then reheating turns the inflaton energy into the hot particles and radiation needed for the next stages. Without inflation, the Big Bang model can describe what happens after those conditions are in place, but it has to assume them. With inflation, those conditions have a possible physical origin. The smoothing effect also helps explain why the universe looks statistically the same in every direction. If inflation stretched a tiny region into our entire observable cosmos, then any preferred direction that existed before could have been diluted. The universe would not carry a strong directional memory within our patch. Observations strongly support this large-scale isotropy. The cosmic microwave background looks nearly identical in every direction, after accounting for local effects, such as our motion through space and emissions from our galaxy. That broad sameness is exactly the sort of thing inflation was designed to explain, but inflation does not require the whole universe beyond our horizon to be identical to our region. This is an important distinction. Our observable universe may be smooth and flat because it came from one inflated patch. Beyond what we can see, there could be regions with different histories, especially in more speculative models. The fact that our visible patch is uniform does not prove that all of existence is uniform. It tells us about the region available to observation. Inflation can make that region large enough and smooth enough while leaving open the possibility of a much larger cosmos beyond it. The idea can feel disorienting because it changes our sense of what is typical. Before inflation, one might imagine the observable universe as a representative sample of all that exists. After inflation, it may be more like a small portion of a much larger expanded domain. We see a smooth patch because inflation stretched it beyond our horizon. There may be far more universe outside our view. It might be similar, it might not. The sky gives us extraordinary information, but it does not give us permission to assume we see everything. Still, the information we do have is rich. The cosmic microwave background supports a universe that is highly uniform with tiny fluctuations. Measurements of large-scale structure support the growth of those fluctuations under gravity. Observations of geometry show near flatness. These independent facts fit together under inflation like pieces of a carefully made puzzle. Not every piece is in place, and some edge pieces may still be hiding under the rug, but the overall image is compelling. One of the gentle ironies of inflation is that it explains the universe's smoothness by making it enormous. Usually making something bigger makes it harder to keep orderly. A small cupboard can be tidy. A whole house is more difficult. A planet full of cupboards is frankly asking for trouble. But inflation works because it begins with a small region and stretches it so much that its local order becomes cosmic order. It does not organize a huge universe by sending instructions across it. It enlarges a region that was already organized enough. This also means that the smoothness we see is not perfect calm, but fossil calm. It is inherited. It tells us about the early connectedness of our cosmic patch. The microwave background is almost uniform because the young universe had once shared conditions across the region that became visible to us. Inflation made that shared state appear across the entire sky. The uniformity is not an accident. It is a preserved memory of closeness before separation. The flatness is similar. It is a memory of stretching. If space once had curvature in our patch, inflation enlarged the patch until the curvature became almost undetectable. Our measurements today find a universe extremely close to flat, but this does not necessarily mean the total universe has no curvature whatsoever. It may mean that our observable region is too small compared with the scale of curvature to reveal it. As with Earth, local flatness can hide global curvature. Inflation makes our local cosmic flatness expected. There is something quietly satisfying about this. The universe appears smooth because it was once close enough to smooth itself. It appears flat because it was stretched until curvature became invisible. It contains structure because quantum fluctuation survived and grew. These ideas do not remove the mystery of why inflation began, but they explain why the universe we observe has the basic features needed for cosmic history to unfold. If the early universe had not been smooth enough, there might have been no stable background for gentle structure formation. If it had not been flat enough, its expansion history might have been dramatically different. If it had not contained the right small fluctuations, matter might never have gathered into galaxies. Inflation creates the conditions for a universe that is both orderly and fertile. It is the difference between a blank page, a torn page, and a page with just enough texture to hold ink. The smoothing and flattening also set the stage for everything that follows in the hot universe. Once inflation ends, the universe is filled with particles and radiation. The tiny ripples begin influencing the plasma. Gravity pulls, radiation pushes, and waves move through the early cosmic material. Later, when atoms form, the cosmic microwave background is released, carrying the imprint of those ripples on a smooth and nearly flat background. Much later, the ripples grow into galaxies. The overall smoothness remains visible in the large-scale distribution, while local clumping creates the structures we inhabit. So inflation is not merely a dramatic burst at the beginning, it is a shaping process. It shapes the geometry of space, it shapes the uniformity of temperature, it shapes the abundance of relics, it shapes the initial pattern of density. It prepares the universe not by building everything directly, but by making the later building possible. It is the early act of stretching that allows the long act of cosmic growth, and this preparation is visible faintly but powerfully in the oldest light. The cosmic microwave background is smooth because inflation smoothed the early patch. It is not perfectly smooth because inflation also stretched quantum fluctuations. Its patterns tell us about the density ripples. Its near uniformity tells us about the shared origin of distant regions. Its relation to the geometry of space tells us that the universe is close to flat. In that ancient glow, the smoothing and the rippling appear together. The canvas and the brushstrokes are both present. That is where the next part of the story naturally waits. If inflation made the cosmos smooth and flat, then the best evidence should be hidden in the light released when the universe first became transparent. That light has crossed space for almost the entire history of the cosmos, cooling and stretching along the way until it became a faint microwave glow. It surrounds us from every direction, a quiet afterimage of the young universe, carrying tiny differences that began as quantum ripples and broad uniformity that points back to inflation's great stretch. To understand inflation more deeply, we must listen to that ancient light, because it is the closest thing the universe has given us to a photograph of its early face. That early face is not a portrait of inflation itself, not in the direct sense. Inflation happened far too early for light from that moment to travel to us as a simple image. The universe was not transparent then. It was not filled with stars shining through space, and there was no clear beam of light carrying news from one place to another in the way we're used to imagining. For a long time after inflation ended, the universe was a dense glowing mixture of particles and radiation, so hot and crowded that light could not travel freely. Photons, the particles of light, were constantly scattered by charged particles. They moved, collided, changed direction, and moved again, like someone trying to cross a busy room while every person in the room insists on stopping them for a very urgent conversation. Only much later did the universe cool enough for light to escape that crowd. Electrons joined with atomic nuclei to form neutral atoms, and once that happened, light no longer scattered so often. The fog lifted. The universe became transparent. The light released at that time has been travelling ever since, stretching along with space, cooling from a hot, visible glow into the faint microwave radiation that fills the cosmos today. This is the cosmic microwave background, the oldest light we can observe directly. It is not the light of inflation, but it carries the imprint of conditions shaped by inflation. It is a photograph of the young universe, and hidden in that photograph are clues about an even younger universe that no camera can ever see. The cosmic microwave background surrounds us from every direction. It is not coming from one special place in space. It is the cooled afterglow of the early universe itself. Wherever we look, beyond the glow of our own galaxy, and beyond the nearer clutter of stars and dust, this ancient light is there. It is almost the same in every direction, which is one of the most important facts in all of cosmology. The universe, at the time this light was released, had nearly the same temperature everywhere. That smoothness is exactly the kind of thing inflation was designed to explain. A small connected region became enormous, and its shared conditions were stretched across the sky. But the light is not perfectly smooth, and that is just as important. The cosmic microwave background contains tiny differences in temperature. Some directions are slightly warmer, some are slightly cooler. The differences are very small, so small that without sensitive instruments the whole sky would seem almost perfectly even. Yet those tiny differences are the beginning of everything interesting. They show where the early universe was slightly denser, or slightly less dense. They are the visible trace of the primordial ripples, the stretched quantum fluctuations that inflation may have written into space. This is why the cosmic microwave background is often treated like a treasure map. It does not show galaxies yet. It does not show stars. It does not show planets, or any of the later structures that make the universe visually dramatic. Instead, it shows the faint pattern from which those structures would grow. It is the universe before it became ornate, a nearly uniform glow, lightly speckled with tiny variations. To an untrained eye, it might look like very subtle mottling. To cosmologists, it is a record of the earliest density pattern we can observe. The temperature variations tell a story about gravity and pressure in the young universe. After inflation ended, the universe was filled with hot particles and radiation. The tiny density differences left by inflation affected this hot plasma. Regions that were slightly denser had a little more gravity, so matter tried to fall inward, but radiation pressure pushed back. The result was a kind of cosmic ringing, enormous waves moving through the early plasma. These were not sound waves in air, because there was no air and no ears, but they were pressure waves through the hot early material. They compressed and rarefied the plasma, leaving a pattern in the radiation that later became the cosmic microwave background. The pattern of these waves is extremely valuable. It tells scientists about the contents of the universe and the nature of the initial ripples. The sizes of the warm and cool patches, the strength of the variations, and the way the pattern changes from larger scales to smaller scales all carry information. The universe, in its early glowing fog, was not silent in a physical sense. It was oscillating under the combined influence of gravity and radiation pressure. When the fog cleared and light escaped, that oscillating pattern was frozen into the microwave background. The ancient light became a record of the last scattering of photons, but also of the earlier ripples that guided the motion of the plasma. Inflation enters this record in two main ways. First, it explains why the background is so uniform overall. Second, it explains why the tiny variations have the particular pattern we observe. The broad smoothness points to a shared origin for widely separated regions. The small ripples point to quantum fluctuations stretched during inflation. Together, they make the microwave background one of the strongest pieces of evidence for the inflationary picture. The first measurements of the cosmic microwave background showed that it existed and that it was remarkably uniform. Later measurements revealed the tiny temperature variations. Still later observations mapped them in greater detail. Each improvement gave a sharper view of the early universe. Instruments carried into space could avoid much of the interference from Earth's atmosphere and measure the microwave sky with remarkable precision. These missions created maps that look like mottled ovals of warm and cool regions, but behind those colours is a vast amount of information. The pattern is not decoration, it is data from the young cosmos. One of the remarkable results is that the universe appears very close to flat. The microwave background helps reveal this because the pattern of temperature variations has a preferred scale, related to the size of the sound waves in the early plasma. If space was strongly curved, that pattern would appear shifted in size, much as an image can appear distorted by a lens. Observations show a pattern consistent with a universe whose large-scale geometry is extremely close to flat. This matches one of inflation's key predictions. Inflation stretches space so much that any initial curvature becomes nearly invisible across our observable region. The microwave background also shows that the primordial ripples were nearly scale-balanced. In simpler words, the early variations had similar strength across a wide range of sizes, though not perfectly identical. This is just what many inflationary models predict. During inflation, quantum fluctuations were stretched to cosmic scales at different times. Because the inflaton field changed slowly as inflation proceeded, fluctuations at different scales could have slightly different strengths. The ancient light preserves that slight difference. It is as if the microwave background remembers not just that inflation happened, but something about how the inflationary engine was changing while it ran. That memory is not a simple voice saying, "Here is the answer." It is a statistical pattern. Cosmologists compare the observed microwave sky with the patterns predicted by models. They do not ask whether one warm spot matches one future galaxy, because that is not how the evidence works. They ask about the distribution of variations across the whole sky. How strong are the large-scale variations compared with smaller ones? How random is the pattern? Are the fluctuations mostly of the kind expected from density variations seeded by a single field? Are there hints of more complicated behaviour? The answers so far fit the basic inflationary picture very well, while still leaving room for debate about the detailed model. This is one reason the cosmic microwave background is so powerful. It lets scientists test ideas about an era that happened long before the light itself was released. Inflation may have ended far earlier, but its effects shape the density ripples. Those ripples influenced the plasma shaped the light. The light travelled across the universe and arrived at our telescopes. In that long chain, the microwave background becomes a messenger from a time it did not directly witness, carrying inherited information from the earlier stretch of space. Polarization adds another clue. Light can have a preferred orientation, and the cosmic microwave background has faint polarization patterns created by the scattering of light in the early universe. Some of these patterns are expected from the same density ripples that created the temperature variations. They have been measured and agree with the overall picture. But there may be another kind of polarization pattern, one that would point to primordial gravitational waves produced during inflation. These gravitational waves would be ripples in space itself, generated by the violent expansion of the earliest universe. If detected clearly, their imprint in the microwave background would be a direct clue about the energy scale of inflation. This possible signal is very faint, and measuring it is difficult. The problem is not only that the signal may be small, it is also that our own galaxy contains dust, and dust can emit polarized light that imitates some of the patterns scientists are searching for. The universe, with its usual sense of humour, placed a dusty foreground between us and one of the deepest clues to the beginning. So researchers must carefully separate local contamination from primordial signals. They compare observations at different microwave frequencies, build models of galactic dust, and use instruments designed to measure polarization with extraordinary sensitivity. It is careful work, slow work, and sometimes frustrating work. But it is also one of the most promising ways to learn more about inflation. So far, the clearest evidence from the microwave background supports the existence of the primordial density ripples, but the special gravitational wave signal remains unconfirmed. That absence is not failure. It tells scientists which inflationary models are less likely. Some models predict stronger gravitational wave signals. Others predict weaker ones, perhaps too faint for current instruments. Each new measurement narrows the possibilities. In cosmology, silence can be informative. If the universe does not show a signal where a model predicts one should be, the model must be reconsidered. The sky answers both by speaking and by refusing to speak. The cosmic microwave background also helps confirm that the early ripples were mostly adiabatic, meaning the different components of the early universe varied together in a coordinated way. This fits naturally with many simple inflationary models, where one dominant field creates the initial density variations. If the early universe had contained several independent sources of fluctuations, the microwave background might show a different pattern. Scientists look for such signs because they could reveal more complicated physics during inflation. So far, the simplest broad picture remains remarkably successful, though the door is not closed to subtler effects. Another feature is that the fluctuations are very close to Gaussian, meaning their statistical distribution resembles the ordinary natural pattern produced by many simple random processes. Strong departures from this would suggest interactions or multiple fields during inflation. Searches for such departures are ongoing. The fact that the observed pattern is so close to Gaussian supports the idea that the ripples came from quantum fluctuations stretched by a relatively simple inflationary process. But again, precision matters. Even tiny deviations, if found, could teach us a great deal about the inflaton field and its interactions. In this way, the microwave background is both simple and rich. Simple, because it is a nearly uniform glow from the early universe. Rich, because its tiny variations contain detailed information about cosmic history. It tells us the universe was hot and dense. It tells us matter and radiation once formed a plasma. It tells us the geometry of space is close to flat. It tells us the early density variations had a particular pattern. It tells us those variations are consistent with inflation. It does all this while being faint enough that, for most of human history, no one knew it was there. The oldest light in the universe spent billions of years passing through everything, waiting for a species with microwave detectors and a taste for difficult questions. There is something charming about the fact that this ancient glow was first noticed as a kind of unwanted noise. A faint hiss in a radio antenna turned out not to be a local problem, not equipment misbehaviour, and not a family of pigeons causing more trouble than usual, though pigeons did have their moment in the story. It was the afterglow of the early universe. What looked like background interference was actually a message from cosmic youth. Science often advances this way, by noticing that an annoyance is too consistent to ignore. Since then, the microwave background has become one of the pillars of cosmology. It is used to estimate the age of the universe, the amount of ordinary matter, the amount of dark matter, and the properties of dark energy. But for our story, its role as an echo of inflation is especially important. It gives us the best observational bridge between the theory of rapid early expansion and the later universe we can see. Inflation predicts the kind of initial ripples. The microwave background displays them. The match is not perfect proof of every inflationary detail, but it is strong evidence that something very much like inflation may have happened. The word echo is fitting, as long as we do not take it too literally. The cosmic microwave background is not sound bouncing off a wall, it is light released from the early universe. But it carries echoes in the sense of preserved influence. Inflation shaped the ripples shaped the plasma shaped the light still surrounds us. The echo has been stretched and cooled by cosmic expansion, but it remains measurable. Every microwave photon from that background is a tiny survivor of the young universe's transparent moment, carrying the imprint of older events. When we look at maps of this light, we are seeing the universe at a time when it had no stars. That alone is worth resting with for a moment. The entire visible cosmos was once a glowing fog, nearly uniform with only tiny differences from place to place. No galaxies, no planets, no heavy elements in the familiar abundance, no darkness between stars because there were no stars and the light was everywhere. The later universe of black space and bright objects had not yet emerged. The microwave background shows a time before the universe became visually dramatic, before gravity had finished turning small differences into glowing structures. And yet the drama was already prepared. The tiny warm and cool regions were not just decoration, They were the early signs of future structure. Denser regions would become the places where matter gathered. Less dense regions would become emptier spaces. Over time, under gravity, the pattern would deepen. The universe would turn from smooth fog into web. The cosmic microwave background is therefore both an ending and a beginning. It marks the end of the opaque plasma era, and it preserves the beginning of visible structure. This is why studying it feels a little like examining the grain of a seed and imagining the forest. The seed is not the forest, but it contains the first instructions for growth. The microwave background is not the universe we live in today, but it contains the early pattern from which today's universe grew. Inflation, in turn, may explain where that seed pattern came from. The chain is long, but it is coherent. Quantum fluctuations during inflation became density ripples. Density ripples became microwave background variations. Those variations became the initial conditions for galaxies. Galaxies became homes for stars and planets. Eventually, one planet produced creatures able to map the microwave sky and be surprised by how well it all fits together. There are still open questions. Scientists do not know which inflationary model is correct. They do not know the exact identity of the inflaton field. They do not know whether inflation was a single event in our cosmic patch or part of a larger process continuing elsewhere. They do not know whether primordial gravitational waves will be detected. They do not know whether subtle non-Gaussian patterns or other hidden features will appear in future measurements. The microwave background has answered many questions, but it has also made the remaining questions sharper. That is one of the marks of good science. The unknown does not disappear, it becomes better defined. Before the microwave background was measured in detail, questions about the earliest universe were broad and hazy. Now they are precise. How strong are the primordial gravitational waves? How slight is the tilt in the fluctuation pattern? Are there tiny statistical deviations from simple inflation? How did reheating unfold? What energy scale drove the expansion? These questions are still difficult, but they are no longer shapeless. The ancient light has given them edges. The cosmic microwave background also reminds us that the universe is observable in layers. The stars we see with our eyes tell one kind of story. Galaxies tell another. The distribution of galaxies tells another. The microwave background reaches deeper still to the young universe before stars, and inflation lies behind even that, inferred through the patterns that survived into the light. We cannot see inflation directly, but we can see its possible consequences. That is often how the deepest parts of nature reveal themselves, not by appearing plainly, but by shaping what does appear. So when we speak of echoes of inflation in cosmic microwave light, we mean that the oldest observable radiation carries signs of an earlier expansion. Its smoothness suggests that distant regions once shared conditions before being stretched apart. Its flatness-related pattern suggests that space was expanded until curvature became nearly invisible. Its tiny temperature variations suggest quantum fluctuations stretch to cosmic size. Its polarization may yet reveal traces of primordial gravitational waves. It is a single glow with many messages folded into it. The calmness of that glow is perhaps the most striking thing. It is everywhere, faint, cold, and almost uniform. It does not flash. It does not announce itself. It does not look dramatic in the sky. And yet it is one of the greatest records available to science. It is the universe whispering about its youth in microwaves. To hear it, we need detectors rather than ears, careful analysis rather than simple sight. But what it tells us is profound. The universe began its visible life with a pattern that inflation can explain, and as the measurements improve, the whisper becomes clearer. New observatories continue to study the microwave background from the ground, from balloons, and from space. They aim to measure polarization more precisely, separate dust from primordial signals, and refine our understanding of the early universe. Each improvement may reveal whether inflation was simple or complex, whether it produced detectable gravitational waves, and whether the inflaton field behaved as our best models suggest. The sky is still being read. For now, the microwave background gives us a strong and beautiful picture. The universe was once a hot glowing plasma. It became transparent, and the light from that moment still surrounds us. That light is nearly uniform because the early observable universe was nearly uniform. It has tiny variations because primordial ripples existed. The pattern of those variations matches the idea that inflation stretched quantum fluctuations across space. The same light that marks the earliest visible surface also points beyond itself, toward a hidden inflationary era. This brings us close to the edge of the known story and toward one final question. If inflation happened once in our region, did it simply end everywhere, neatly and completely, leaving behind one universe like ours? Or is inflation, in some deeper sense, difficult to stop? Could it end in some places while continuing in others? Could our observable universe be only one settled region in a far larger inflating reality? The microwave background shows us the afterglow of our own cosmic beginning, but the theory that explains it may open a door to something even wider, a possibility that the end of inflation here was not necessarily the end of inflation everywhere. That possibility takes us to one of the strangest edges of inflationary cosmology, because inflation may not behave like an ordinary event with one clean beginning and one clean ending everywhere at once. In the simplest picture, the inflaton field drives a brief period of rapid expansion, then changes state, releases its energy, fills the universe with hot particles and radiation, and the familiar cosmic story begins. That is already strange enough. It gives us a universe that was stretched smooth and flat, seeded with quantum ripples, and reheated into the bright early plasma whose afterglow we still observe as the cosmic microwave background. But when scientists examine some versions of inflation more closely, the story develops a curious extra possibility. Inflation might end in some places while continuing in others. This idea is called eternal inflation, though the name should be handled gently. It does not necessarily mean that every part of reality inflates forever in the same way. It means that, in certain models, once inflation begins, the process may keep going somewhere, even while it ends in many individual regions. Our observable universe would be one region where inflation ended. The inflaton field changed state here, reheating occurred here, matter and radiation appeared here, and the long history leading to galaxies, stars, planets, and sleepy discussions of cosmology unfolded here. But beyond the region we can observe, there may be other places where inflation continued longer, or ended later, or perhaps is still going on. The key to understanding this is that the inflaton field is not perfectly still. Like all quantum fields, it can fluctuate. In the ordinary inflationary story, the field slowly changes until it reaches the condition where inflation ends. But quantum fluctuations can nudge the field differently in different regions. In one patch, the field may roll down and end inflation. In another patch, a fluctuation may push it back up or keep it in the inflationary state longer. Because regions that remain inflating expand incredibly quickly, they can create more inflating space even as some portions stop inflating. It is like a strange cosmic process, where pockets finish inflating and become hot universes, while the background continues stretching and producing still more pockets. An everyday comparison is difficult because everyday life contains very few examples of rapidly expanding space with quantum fields inside it, which is probably for the best. But imagine a pot of water beginning to boil, not because the physics is the same, but because the pattern gives us something to hold. Bubbles form in different places. A bubble is a region where the state of the water has changed from liquid to vapor. Around it, the liquid remains. More bubbles appear elsewhere. In eternal inflation, the inflating state is more like the surrounding medium, and the regions where inflation ends are like bubbles forming within it. Each bubble becomes a hot Big Bang region, a place where the inflaton energy transforms into particles and radiation. Our universe could be inside one such bubble. This image is useful, but it is also easy to misuse. These bubble regions are not floating through ordinary space like soap bubbles in a room. The surrounding space is itself inflating. The bubbles are regions of space where inflation has stopped and normal expansion has begun. The distances between such regions can grow so quickly that one bubble may never be able to communicate with another. If other bubble universes exist, they may be forever beyond our observational reach. We would not simply point a telescope far enough and see one glowing next door. The expansion between us could make contact impossible. This is where the idea becomes both fascinating and frustrating. Eternal inflation can arise naturally in some theoretical models, but it is difficult to test directly. Science is most comfortable when an idea makes predictions we can check. Inflation itself has observational support because it explains the smoothness, flatness, and pattern of tiny fluctuations seen in the cosmic microwave background. Eternal inflation goes a step further. It may be a consequence of some inflationary models, but the other inflating regions or bubble universes would likely lie beyond our cosmic horizon. That makes direct evidence hard to obtain. Still, scientists take the idea seriously because it comes from the same physics used to describe inflation. It is not just an idle fantasy added for decoration. In some models, the inflationary state is very hard to end everywhere because quantum fluctuations keep parts of the inflaton field high enough to continue driving expansion. Regions where inflation ends become large, but regions where it continues grow even faster. Over time, the total amount of inflating space can increase. That is the sense in which inflation becomes eternal. Locally it can end, as it did in our observable region, but globally it may continue without a final overall stop. This produces a very different picture of the universe. Instead of one single hot Big Bang region containing everything, there may be a much larger inflating reality that constantly gives rise to many regions like ours. Each region begins when inflation ends locally, and reheating fills that region with particles and radiation. Each could have its own observable universe from the viewpoint of any beings inside it. Some might have physical conditions similar to ours. Others might be very different depending on the details of the fields involved. The word universe becomes slippery here. Sometimes people use it to mean everything that exists. Sometimes they use it to mean our observable region. In eternal inflation, it's often clearer to speak of our observable universe as one region within a much larger whole. This naturally leads to the idea of a multiverse. That word can sound like science fiction, and it has certainly been borrowed enthusiastically by science fiction, comic books, and anyone who wants to explain why 3 versions of the same character are now sharing a sandwich. But in cosmology, the multiverse idea connected to eternal inflation has a specific meaning. It suggests that inflation may produce many separated regions, each with its own hot Big Bang phase. These regions could be so far apart, and the space between them could be expanding so fast that they cannot interact. They would be parts of a larger physical reality, but not part of one shared observable cosmos. The speculative part becomes even larger when scientists ask whether different regions could have different laws or constants of nature. In some theories, especially those involving complicated high-energy landscapes, the fields that settle after inflation might end in different states in different regions. Those states could affect particle masses, forces, or the value of vacuum energy. If that is true, then different bubble universes might not merely contain different arrangements of matter. They might have different physical properties. Some might allow galaxies and stars. Others might expand too quickly, collapse too soon, or have particles that never form atoms. We do not know whether this picture is correct, but it is one reason eternal inflation has attracted so much attention. There is a delicate balance in discussing this. The idea is scientifically motivated but not confirmed. It is tempting to treat the multiverse as though it were already an observed fact, but that would go too far. We have not seen another bubble universe. We have not measured a signal from an inflating region beyond our horizon. The evidence we have supports inflation in broad terms, especially through the cosmic microwave background, but eternal inflation remains more speculative. It may be a natural outcome of some models. It may be avoided in others. Future theory and observation may strengthen or weaken the case. One possible observational clue would be evidence that our bubble collided with another bubble in the distant past. If two bubble regions formed close enough in the inflating background, a collision might leave a pattern in the cosmic microwave background, perhaps a circular feature or some unusual asymmetry. Scientists have looked for such signs. So far, no convincing evidence has been found. That does not prove other bubbles do not exist. It may simply mean that no collision occurred within our observable region, or that any signal is too faint or too confused with other effects. But it shows how cosmologists try to make even speculative ideas face the sky and answer questions, sir. Another clue could come from more precise measurements of inflationary signatures. If we detected primordial gravitational waves, or found subtle statistical features in the microwave background, we might learn more about the shape of the inflaton field and whether it belongs to a class of models that favours eternal inflation. Again, this would not necessarily show other universes directly. It would strengthen or weaken the theoretical path leading to them. Much of early universe science works this way. The deepest events are not observed directly. Their reality is inferred from patterns, consistency, and the way multiple lines of evidence point toward the same underlying process. The question of whether inflation ended everywhere also touches the problem of probability. If eternal inflation produces many bubble regions, perhaps infinitely many in some descriptions, then scientists face a difficult question. How do we predict what a typical observer should see? If every possible outcome happens somewhere, how do we assign probabilities to observations in our region? This is known as a measure problem, though the name is less cozy than the issue deserves. The basic difficulty is that infinities are hard to compare. If there are infinitely many regions of one kind and infinitely many of another, saying which is more common becomes tricky. Cosmologists and philosophers of physics still debate how to handle this. This may sound far removed from the calm glow of the microwave background, but it matters because a theory should ideally explain not only what can happen, but what is likely to happen. Inflation works well when it predicts the pattern of fluctuations in our universe. Eternal inflation becomes harder because it may produce such a wide range of outcomes that prediction becomes less straightforward. This is one of the major criticisms of the idea. If a theory becomes too flexible, it risks explaining everything after the fact and predicting too little in advance. Supporters argue that the underlying models can still have testable consequences. Critics argue that caution is needed. This debate remains active. There is also the question of the beginning. If inflation can be eternal into the future, was it eternal into the past? Did it always exist, with bubble universes forming forever? Many studies suggest that inflation, even if eternal toward the future in some regions, may still require some kind of beginning or boundary in the past. The details are subtle and depend on assumptions about gravity, quantum physics, and the meaning of time at the earliest moments. We should not pretend this is settled. The origin of inflation itself remains one of the deepest open questions. Eternal inflation may extend the story outward and onward, but it does not automatically explain why there was an inflating state in the first place. This is a recurring pattern in cosmology. An idea solves one level of mystery and reveals a deeper one. Inflation explains why the observable universe is smooth, flat, and seeded with the right kind of ripples. Then we ask what caused inflation. The inflaton field explains how rapid expansion might be driven. Then we ask why that field existed and why it began in the right state. Eternal inflation explains how inflation might continue somewhere while ending here. Then we ask what sets the larger conditions of the whole inflating reality. The questions do not disappear. They move deeper, like someone tidying a room by opening a closet and discovering another room behind it. Even so, the idea that inflation may still be happening somewhere changes the emotional scale of the story. Our universe already feels enormous. The observable universe contains hundreds of billions of galaxies, each with immense numbers of stars. Light from the edge of what we can see has crossed space for nearly the entire age of the cosmos. That is vast enough for any reasonable bedtime thought. But eternal inflation suggests that our observable universe may be only one region in a far larger process. Perhaps one bubble among many, perhaps one local ending in a sea of ongoing expansion. It is a humbling idea, and humility is something cosmology provides in generous quantities. If inflation is still happening elsewhere, those elsewhere regions are not places we could travel to in any ordinary sense. The space between us and them would not merely be large, it may be expanding in a way that prevents contact forever. Even light may never bridge the gap. The phrase somewhere can therefore be misleading. In everyday language, somewhere means a place you could, in principle, reach with enough time, fuel, snacks, and poor judgment. In eternal inflation, somewhere may mean a region of reality outside our causal future, forever disconnected from us. It exists in the theoretical structure, but not as a destination. This also means that our observable universe could be only a tiny part of the aftermath of a local end to inflation. Everything we know, from the cosmic microwave background to the most distant galaxies, belongs to our post-inflationary region. Our laws of physics, as measured here, describe this region. The microwave background tells us about our early hot phase. The distribution of galaxies tells us how our density ripples grew. We can reconstruct our own cosmic history with impressive success. But if eternal inflation is correct, there may be other histories beyond observation, written in regions we will never see. Some people find this unsettling because it places parts of reality beyond possible contact. But science already deals with horizons. We cannot see beyond the observable universe, even in the standard picture. We cannot observe inside a black hole beyond its horizon. We cannot directly see inflation itself. Yet we can reason carefully from what is visible. The key is not to confuse possibility with proof. Eternal inflation is a serious possibility in some models, but it remains less established than the broad inflationary explanation for our observable universe. The best approach is curiosity with discipline. Wonder, but keep your measuring instruments nearby. There is another way to think about the question of whether inflation ended. For us, it did. That much is built into our existence. If inflation had not ended in our region, there would be no hot plasma, no cosmic microwave background, no matter clumping into galaxies, no stars, no planets, no quiet rooms where someone listens to a science video while the day fades out. Our region made the transition. The inflaton energy changed into particles and radiation. Expansion slowed from its inflationary surge into the more familiar cosmic expansion. The universe cooled, atoms formed, light travelled freely, and structure grew. In the only region we can study directly, inflation is over. The deeper question is whether our local ending was part of a complete global ending or just one local transition among many. A simple inflationary model may end everywhere in the relevant region, leaving one enormous universe with shared conditions. An eternal inflation model lets different regions end at different times, while other regions continue inflating. Both pictures agree that inflation ended here. They differ in what lies beyond our observable horizon and in the larger structure of reality. Because we cannot directly observe beyond our horizon, the decision between these pictures depends on theory and indirect evidence. Scientists ask which models best fit the microwave background. They ask which models naturally arise from high-energy physics. They ask whether the models make predictions that can be tested. They examine whether eternal inflation creates conceptual problems or solves deeper ones. This is not a finished argument. It is an active frontier. And frontiers in science are rarely tidy. They contain good ideas, wrong turns, clever calculations, uncomfortable questions, and occasionally coffee that has been reheated too many times. What makes the question so rich is that it links the smallest physics to the largest possible reality. The quantum fluctuations of a field may determine whether inflation ends in one place or continues in another. The behaviour of the inflaton field may shape not only our observable universe, but a much larger cosmic landscape. The same physics that made tiny ripples in the microwave background could, in some models, create whole regions beyond our reach. Once again, inflation connects the microscopic and the immense. It also changes how we think about beginnings and endings. We usually imagine an event ending as a simple thing. A song ends, a candle burns out, a kettle boils and then, if ignored, becomes a small domestic problem. But cosmic inflation may end locally rather than universally. The end is not necessarily one moment across all existence. It can be a transition in a region. Here, inflation ended. Elsewhere, perhaps it continues. Farther away, perhaps it ended earlier or later. The word end becomes less absolute and more geographical, though even geographical is not quite right when space itself is part of the story. Our best evidence remains close to home, cosmically speaking. We have the ancient microwave light. We have maps of galaxies. We have measurements of expansion, matter, radiation, and geometry. These tell us that our universe began its visible history hot, dense, smooth, and lightly rippled. Inflation explains why. The possibility of eternal inflation extends the explanation into a larger speculative framework. It may be true. It may be partly true. It may be replaced by a deeper theory that keeps some of its insights and changes others. That is how science often moves. Today's frontier becomes tomorrow's foundation or tomorrow's cautionary tale. For now, the safe and beautiful statement is this. Inflation appears to be a powerful explanation for the early conditions of our observable universe. It likely ended in our region by transferring the energy of the inflaton field into the hot particles and radiation of the Big Bang phase. In some versions of the theory, inflation may continue elsewhere, producing other regions beyond our horizon. We do not know whether those regions exist. We do not know whether inflation is truly eternal. But the possibility follows from serious attempts to understand the physics of the earliest cosmos, and so the story leaves us with a universe that is both more knowable and more mysterious than before. We can measure the oldest light, we can map tiny ripples, we can infer the smoothing and flattening of space, we can describe how quantum fluctuations became seeds of galaxies, we can follow the long path from hot plasma to stars and planets. At the same time, we are left wondering whether our entire visible cosmos is only one calm pocket where inflation ended, while beyond all possible sight, space continues its rapid growth, making room for other beginnings we will never see. That thought does not need to be rushed. It can sit quietly for a moment. Somewhere beyond our horizon, if the theory is right, inflation may still be continuing. Not somewhere in the sky that a stronger telescope could simply reveal, but somewhere outside the reach of contact, in the larger structure of reality. A universe would be one finished breath in an ongoing process, a region where the stretching slowed, the heat appeared, the light eventually escaped, and the ripples grew into galaxies, and here we are, very late in that local story. We are not in the inflationary fire, we are not in the first glowing plasma, we're not even in the first age of stars. We live in a mature universe, with galaxies already old, heavy elements already forged, planets already formed, and minds already capable of tracing everything backward. The fact that we can ask whether inflation ended everywhere is itself a result of inflation ending here. The question depends on stars, chemistry, time, and the slow formation of worlds. So as this journey settles, we can return to the simple image where we began. The early universe was once a tiny connected patch, then space stretched with astonishing speed. That stretch made the cosmos smooth and flat. Quantum fluctuations became the ripples written into ancient light. The inflaton field, hidden but powerful, may have driven the expansion and then released its energy into the hot young universe. The cosmic microwave background still carries the afterimage of those beginnings. And beyond our view, perhaps, inflation did not stop everywhere. Perhaps it is still unfolding in regions forever out of reach, Whether that final possibility is true remains one of the great open questions, but the part we can see is already remarkable enough. A brief early stretch may have shaped everything visible. The smallest fluctuations may have become the largest structures. The oldest light may preserve echoes of an event that happened before light could travel freely. And the universe, for all its immense age and scale, may still carry the memory of an instant when space grew faster than imagination can comfortably follow. Wherever you're listening from tonight, your little corner of the cosmos is part of that history. The room around you, the air, the quiet screen glow, the atoms in your body, the stars beyond the window if the sky's clear, all belong to a universe that once passed through a very strange beginning. Inflation may be over here, but its consequences are not. They are in the smoothness of the sky, in the structure of galaxies, in the ancient microwave light, and in the fact that there was enough time and space for this moment to exist at all. Sleep well, fellow traveller, in this cooled and settled region of a universe that may once have grown from almost nothing into everything we can see.